everyone. We are about to start the formal synthesis session. So we have 5 talks today. So the first speaker is Justin Lubin, PhD student at Berkeley, and he will talk about programming by navigation.
Thank you so much. Hello, everyone. I am very excited to be here today to talk to you about a project that I've been working on called Programming by Navigation. Much like structure editors prevent syntactic mistakes, programming by navigation will prevent semantic mistakes. And I want to tell you a little bit about how we achieve that in the rest of the talk. So I'll start from the observation that in traditional program synthesis, guarantees are going to operate on just one round of interaction. So maybe we give the synthesizer some kind of specification, and we'll get back an expression. And we can prove things about it like soundness, which is that that returned program is going to satisfy the specification, or completeness, which is that a program is going to be returned when a satisfying solution to the specification exists. But what if we want to refine phi? Maybe because the expression that we got back is not exactly the one that we wanted. Well, we can give an updated specification to the synthesizer and maybe get a new expression, and that might be the one that we want. But what kinds of guarantees can we get on this interaction as a whole? Now, this is a much less explored question in the program synthesis literature, but a typical property that folks might prove is something like convergence, which is that the user will accept the synthesis output in a finite number of rounds. Now, of course, this is going to require some pretty heavy assumptions on what the user is doing. In particular, it can actually be quite hard to nail down exactly what the requirements that we're putting on the user is and the guarantees that we're going to be getting. But luckily for us, Peleg and colleagues recently published this paper on an abstraction-based interaction model for synthesis, where they give a very general language for talking about exactly what assumptions on user behavior we're requiring in order to get these kinds of convergence guarantees. And the point that I'd like to make with these slides is that it can be actually quite challenging to meet all of these user correctness requirements in practice as a user, and that convergence might not necessarily be the guarantee that we would want. And to make that a little bit more concrete, I'm going to give you 3 stories of what could go wrong. First, the user's refined specification could simply be unsatisfiable. Second, the synthesizer could render valid expressions inaccessible to the user. And lastly, the user could go down a rabbit hole of refining their specification over and over again, but never reaching the program that they would actually want. So instead of this convergence perspective, we're going to propose strong completeness and strong soundness. And this is the image that we like to use to describe these properties. The way that it works is that each of these white nodes is going to be an intermediate program, and each of the green stars is going to be a valid solution to the user's initial specification. Then we're going to have these arrows between the different nodes that are going to represent program transformations, things like edit actions in IDEs or tactics in a theorem prover. We'll start the interactive process from this center expression right here. And rather than requiring that the synthesizer is going to give us back an expression, we're going to require that it gives us back the set of steps that could lead to a valid solution, which I've highlighted in purple here. And this is a property that we'll call strong completeness. Additionally, if we take a look at these other steps right here that I've highlighted in gray, we see that if the user were to take any of those steps, they'll enter a part of the program space where they'll never actually be able to navigate to a possible valid solution. Or in other words, that they'll have gone down a rabbit hole. So in addition to these purple steps, we're going to require that the synthesizer does not show these gray steps to the user, which is a property that we'll call strong soundness. Then the user can select from any of these purple steps that we have right here, for example, sigma A, update the current working expression using that step, and repeat the process until they arrive at the valid solution that they want. So for the rest of the talk, I'd like to answer 2 questions, the first of which is what exactly are strong completeness and strong soundness? And secondly, how can we achieve strong completeness and strong soundness in a realistic program synthesis setting? So let's start with the first one. As I alluded to earlier, steps are going to be the building block for strong completeness and strong soundness. We'll start with an abstract notion of expressions as well as steps. And then we'll also need some sort of notion of validity on expressions. For example, satisfying input-output examples or a logical specification. Then we're going to assume that there's going to be a step relation, which we'll write sigma steps E1 to E2, also written as sigma applied to E1 is going to be equal to E2, as well as an induced binary relation E1 less than E2, where we simply drop the sigma label. And steps are going to be required to satisfy some mild conditions, such as being deterministic, but not super important for this talk, and the details are in the paper, so I'm going to gloss over it here. Then step providers are going to take the place of synthesizers. In particular, we're going to have a step provider and a step decider, where the step provider is going to provide sets of steps to the step decider, which could be something like the user. And the step decider will choose among those steps, update the working expression with that step, and repeat the process as many times as is necessary to reach the valid solution. Formally, a step provider S is going to map expressions to step sets, and an S interaction is going to be a finite sequence of steps such that each step is going to be selected from the previously provided set of steps. And we'll also assume that our starting program, E0, is going to be a designated blank program, which could, for example, just be a program with a hole in it. OK, now we can finally begin to state the programming of a navigation synthesis problem, which is going to define strong completeness and strong soundness. But to do so, we need one more auxiliary definition, which is that the completion of an expression is going to be the set of expressions, valid expressions, that are reachable from it. So for example, the completion of this expression in the center is going to be all 5 stars, whereas the one in the top right is just going to be stars 1 and 2. Now, a step set is going to cover an expression if it satisfies strong completeness and strong soundness. And these are the 2 most important definitions in the talk, so I'd really like to draw your attention to them. Strong completeness is going to be this property right here, which states that if a valid expression is reachable from the current working expression, then there needs to exist a step in the provided step set such that when taken, there's going to be, that valid expression is still going to be reachable from the resulting expression, with the possible exception of the current working expression itself. Strong soundness is going to be this property right here, which states that no matter what step you take, you're always going to have at least one valid expression that's going to be reachable from the resulting expression. Or in other words, that you're not going down a rabbit hole. Then we can say that a step provider S is going to solve the programming by navigation synthesis problem if S of E of n is going to cover E of n for all S interactions that are ending in E of n. So strong completeness and strong soundness are going to be properties of step providers in programming by navigation, and in particular that they must show all and only the valid next steps. That's the answer to our first question. Now let's talk about our second question, which is how we can actually achieve strong completeness and strong soundness in practice. So the domain that we're tackling in the paper is component-based synthesis with top-down steps. In particular, we're going to have types, functions, and validity conditions on these functions that specify semantically when they're going to be valid to apply. So types are going to be black boxes, as is typical in component-based synthesis, but we're also going to annotate them with what we call metadata values. And metadata values are going to be values of simple types like integers, strings, and booleans that can provide additional information about the type. So you can think of these as a very lightweight version of dependent types. To make these types a little bit more concrete, I'd like to give 2 examples from domains that we're really excited to apply programming by navigation to, namely biological data analysis as well as geospatial data analysis. The details of these domains don't matter for the rest of the talk, but it's more to just give you a flavor of the kinds of things that we can model with these types. So for example, for biological data analysis, R of 2 could be the type of an integer vector, where each entry is the number of times that a particular RNA transcript is going to appear in a tissue that's labeled sample number 2. In other words, the metadata value is going to be acting as a label for the underlying data. In geospatial data analysis, R of 90 could be something like the type of a geospatial raster image with a spatial resolution of 90 meters squared per pixel. So in other words, the metadata value is going to be describing the resolution of the underlying geospatial image. Functions could then look like this and be things like performing RNA-seq quality checks or downsampling the raster image. And validity conditions are going to specify when we can call these kinds of functions. So for example, in the case of the quality checks, we're going to require that the output label is going to be equal to the input label on the type. So a simple validity condition. And for downsampling the raster image, we're going to require that there's going to be more meters squared per pixel in the output of the downsampling than in the input of the downsampling. So it's going to be less precise. And here's one such library that we could build up out of many that you could possibly imagine. This is the library that I'm going to be working with for the rest of the talk. It's adapted from one of the benchmark examples that we have in the paper. The exact details of this library don't matter too much, but this is just the sort of flavor of the things that we're going to be working with. OK, so the last thing that we need is we need to define a notion of validity for this setting. And we're going to do that via a well-typing judgment for expressions. At a high level, expressions are either going to be function applications or holes. And function applications are going to be well-typed when the function's validity condition is met. Only ground terms are going to be well-typed because we can't tell whether or not these validity conditions are going to be hold if some of the arguments are going to hold if some of the arguments are holes. So this is the typing judgment that we're going to use for the validity condition, and we're going to return to it later in the talk, so I'd just like to highlight some of the most important parts of it. First, if we look at the conclusion, we can see that this is only going to be well-defined for function applications and not holes. And also, I have this superscript v down here, which is just going to be my notation for annotating what the metadata value is on the return type of that function. Next, this premise right here is going to recursively require that all of the arguments are going to be well-typed, and thus that they are all also going to be function applications. Finally, this condition right here is where we get our sort of semantic constraints for our program synthesis problem, which is going to say that the validity condition on the function needs to hold with the metadata values on all of its argument types as well as its return type. Okay, so now let me give you an example of what this would actually look like in practice. We're going to start with some goal type and a blank working sketch right here. And the idea is that the synthesizer is going to need to return all and only the valid next steps. In this particular case, for the library that I flashed on screen earlier, there's actually only going to be one step, which is going to be replacing hole 1 with d of a new hole, hole 2. So the user can select that step, update the current working expression, and now we have a new goal. Now, it turns out that there's actually exactly 2 valid next steps that the user can take, and we're requiring that the synthesizer is going to show that. So we could either select replacing hole 2 with C or hole 2 with B applied to a new hole. And this process can repeat as many times as is necessary. So in particular, just to emphasize, the synthesizer needs to do this part, and then this user gets to choose among these different valid expressions, and they are guaranteed to be sort of complete in the sense that they're not missing out on any possible choices that they could be taking, and they also have the assurance that no matter which of the steps that they take, they're perfectly valid and they're not going to go down a rabbit hole. Okay, so now, how do we actually do this? Okay, so I want to start by saying that we can't just look at the grammar that's induced by the simple types. So I've reproduced this image from earlier, but now I have hole 1 in the middle, and we need hole 1 to be of type D. If we look at this expression of type D above here, we can see that the simple types line up, and structurally it might be able to fit. But if we actually look at the diagram, we can see that there's no valid solutions down that path. And so it would actually be incorrect to show this to the user, even though things look like they might actually line up. So in some sense, we're requiring that the synthesizer knows where all of these green stars are ahead of time before being able to show the correct steps to the user. Okay. So if we need to know where all of these solutions are, maybe we can enumerate them and store them in some sort of trie-like data structure. And that would work really well if we had a small number of solutions that we could enumerate very quickly. But it's very easy to end up in a situation where there's infinitely many solutions, and so you simply can't represent this. In fact, the library that I showed earlier has infinitely many solutions. Also, our benchmarks show that in practice, this enumerative approach doesn't scale well when you have a large number of solutions. So what are we to do? Well, what we really want to do is we want to extend this well-typing judgment to non-ground terms. In particular, if we look at this premise right here, it requires that all of the arguments are going to be well-typed function applications. But what we want to say is that either it's going to be a well-typed function application, or it's a hole, and there exists an expression that we can slot in there such that the rest of the premise holds. Unfortunately, that existential makes type checking very much not syntax directed, and we end up into this mess that I was talking about with the enumeration that we had earlier. But there's actually a key insight in this observation, which is that what we need is a type inhabitation oracle. Something that, when asked if a type is inhabited, is going to respond yes or no, as in classical logic, without needing to say what that inhabitant is, as you might see in something like constructive logic. So now, for the last technical trick of my talk, I'd like to talk about how we can actually implement one of these type inhabitation oracles. And the high-level idea is that we can use the Curry-Howard correspondence. So we're going to represent types as propositions that are going to be true if inhabited, and expressions as proofs. From this perspective, what the oracle needs to do is determine if a proposition is true or false, but crucially, we don't actually need to know a proof of the proposition, just its truth value. What that means is that we can use a proof engine that doesn't give proofs, something like Datalog. So to give you a very tiny example of the kinds of proof rules that we're going to be generating and dispatching to Datalog, we can take this function that I had from before that was the downsampling operation in the geospatial analysis, and we're going to compile it to this rule right here, where the premises are going to be drawn from the parameter types of the functions as well as its validity condition, and the conclusion is going to be drawn from the return type of the function. Then, critically, we can prove this key invariant right here, which states that for any function f, Datalog is going to prove that tau v holds with a derivation tree ending in rule f, if and only if there exist expressions, E1 through En, such that when f is applied to them, the resulting expression is going to be well-typed. And so this is exactly what we need, because now we can know that these expressions exist without actually finding what they are. Now, there's a lot of wrinkles in this overview. The paper irons them all out. In particular, we need to be able to handle sketches with multiple interdependent holes, and we need to know just a little bit more about what these witness expressions are without actually finding what they are. And so we're generating correspondingly much more complicated proof rules as well as key invariants. But this really illustrates the sort of key insight of what makes this all work. Okay, so strong completeness and strong soundness, how do we achieve them in practice? We can use a classical style inhabitation oracle, and we can leverage the Curry-Howard correspondence to implement it with Datalog. Now I'd like to wrap up. We implemented a programming navigation synthesizer in a tool that we call Honeybee, and we also implemented that enumerative baseline that I mentioned earlier, both a naive version that simply does raw enumeration, as well as a pruning version that actually prunes the search space as it goes, so it's a little bit more sophisticated. For benchmarks with finitely many solutions, Honeybee outperforms both of the baselines, but more interestingly, for benchmarks with infinitely many solutions, the two baselines can't even represent the possible solutions to the benchmark, whereas Honeybee has no problem whatsoever. We also did a scalability analysis and observed that the baselines suffer from this combinatorial explosion, whereas Honeybee does not. So that is programming by navigation. This is the image that I like to have in my head when I think about it, and I'd like to share some concluding thoughts with you all. First, strong completeness and strong soundness are very strong guarantees, and they're not going to be achievable in every domain. In fact, even in something like System F, type and habitation is undecidable, and so the approach that I outlined in this talk provably cannot extend to that domain. Therefore, I think that there's always going to be room for new and exciting interactive program synthesis guarantees. But nonetheless, I do think that strong completeness and strong soundness can be a helpful North Star as we're designing these guarantees. Additionally, even if you're looking at a problem and it seems like it might be too messy and intractable to guarantee these kinds of strong completeness and strong soundness guarantees, you might be surprised. Bit of a story time, but for the past few years, I've been working really closely with wet lab biologists who are producing a lot of very interesting and complex data in the wet lab, but don't necessarily have the background to analyze it themselves. I invented strong, oh, and here's a picture of me in the wet lab learning a lot from them. So I invented strong completeness and strong soundness because I realized that these were the exact guarantees that we would need for a synthesizer to get them the programs that they needed. I wasn't sure whether we'd be able to deliver on these strong guarantees or not, but in the end, we sort of made it work. So I'd encourage you, if you are similarly dealing with a messy problem, to think that maybe strong completeness and strong soundness is actually something that you can achieve. The second point that I'd like to say is that classical style and habitation oracles like Datalog are very, very powerful for synthesis if you can get away with it. So next time you're tasked with determining whether or not an existential is satisfiable, ask yourself whether you really need a witness for that existential or if you can get away with something like Datalog. Next, I'd just like to say that I'd love to collaborate with folks. I'm really excited by programming by navigation as well as adjacent topics. We've observed connections to structure editors, theorem provers, rewrite systems, eGraphs, and I'm excited by all of those and more. And also just taking a step back, Honeybee and many other programming languages tools are based on constraint systems, and I'm very interested in developing new programming language theory to make these systems more usable. With that, I'd like to thank my collaborator Parker Ziegler, who, by the way, is giving a talk tomorrow at PLDI on direct manipulation programming systems, as well as my advisor, Sarah Chasins. And thank you all so much for listening. I'm more than happy to take any questions.
So if I understand correctly, so the one application for this.
Can everybody hear me? Okay. So one application for this framework is what you presented is trying to find a term that is inhabited by the type, right? So do you think it can be applied to other synthesis settings where constructing a type may not be plausible? For instance, if you're trying to find a program that manipulates like string synthesis program, but like trying to construct a program that manipulates the string by interactively. So I think it can be adapted to this situation, program by navigation. So can you further extend this work for other settings instead of like type system?
Yeah, absolutely. That is a fantastic point. So the sort of first half of the talk that I was talking about, where we have this image right here, and we're talking about this sort of program space, this completely works in an untyped setting. We just define a particular notion of validity that uses a type system, as well as these sort of like metadata annotations on these different types. But there's nothing about the framework that you can't model these sorts of situations, something like a string processing domain. Yeah, I'd be super curious to see like what kinds of oracles or other sorts of things that we could build to achieve those kinds of guarantees for that domain. Thanks.
Thanks for the great talk.
Oh, thank you.
Thanks for an interesting talk. So you mentioned classical style in habitation, but you're using Prolog, which I think every time you run it, it's going to find a solution.
We're using
and so that feels very much like constructive.
Yeah, we're using Datalog.
Datalog, yes. Sorry, did I say Prolog? But Datalog is the same. It searches to find a solution.
Sure. Yeah. So it's going to determine whether or not these like facts are going to be inhabited, but it's not going to give us a proof of those facts. So we're not going to be like extracting the provenance from the Datalog. So Yeah, the provenance is a sort of like constructive bit that I was talking about. You could imagine also using something like an SMT solver, which you could use, I guess, to get a proof, but also just going to determine whether or not propositions are going to hold.
Okay. So in principle, it's there, but you're not using it. You don't need to use it.
The data log engines don't typically provide provenance by default because it slows things down a lot.
Got it. Okay, thanks.
Yeah.
So a quick follow-up. When you don't have a star along a branch,
Yes.
then the data log might search forever.
Yeah, so that's very interesting. So we're going to be working over restricted value domains where there's going to be finitely finite values that could slot into the different facts for data log. And so then in that situation, data log is actually guaranteed to terminate because there's only so many facts that you can have over them. So yeah, the sort of data log provability is also going to terminate.
Got it. Thank you.
Thanks. Those are great questions.
Thanks. We stop that. So thanks the speaker again.
So hi everyone, my name is Yuan Tianding, and today I'm presenting our work titled A Concurrent Approach to String Transformation Synthesis with Xiaokang Chuan from Purdue University. And let's first introduce a bit about syntax-guided synthesis. Syntax-guided synthesis is a process that aims to automatically find a program that satisfies a certain specification. Normally there are two inputs for cycle solver. The first one is semantic specification, which defines the program should do, and another one is syntactic information, which describes what the program should look like. Normally use a context-free grammar, and the cycle solver normally just takes those two inputs and generate a solution. The application for syntax-guided synthesis are like spreadsheet programming, and like computer-aided education, complex supermodulation, and loop invariant discovery. And for the SMT solvers, a cycle solver also supports a range of theories, including CLIA, bit vector, and string. And for methods to solve cycles problem, we often use enumeration, deduction, and learning-based methods. And it's a quite active field of research. In past 15 years, researchers have built a lot of solvers in cycle solving, like Flashfield, Sketch, and CVC5, and a lot of others. And researchers have also made a lot of improvements to existing solvers. Like for example, for the ICFP benchmark, at the year of 2015, only 1 of 50 benchmarks can be solved. But now solvers can solve all of them. So likewise, the Hike-Delight benchmarks. Despite the existing process of cycle solver, we still find some problem with string transformation synthesis challenging, even though it's already a well-researched field. So let's first look at a motivating example. In this example, we need to standardize addresses from different countries. Each address must follow the same format, which is country/region/city/street/unit. As highlighted, some address may or may not include a unit number, which will add a little bit complexity here. And the solution should be quite simple. It first splits the examples into two parts, in two cases, and then just rearrange them with with all those comma-separate components. However, surprisingly, this simple task is not solvable by existing cycle solvers, including CVC5 and Flashfield++. So let's discuss the problem. So the first challenge is the number of operators. For string, you have a lot of operators available, like concatenation, substring, and replace. And for list line, and if you have list line integers with a string, you will have some other operator like join, index, and format int. And even for a single, and even for this is only just standard operator, you will have some other operators like domain-specific operator, dates, time, and floats, etc. And even for a single operator, you will have a lot of different way to split the problem, which is P1. Like for concat, you may like have a lot of way to divide the problem. Like the P2 and P3 two problem, you may split before the slash and after the first slash. And like some other problem like P5, you may split the second example but ignore the first. Because all those different way of split, it's quite challenging for Segwit solver to get this problem solved and make the search space quite large. So because of this problem, we propose to utilize concurrency to rescue, by which we mean to use enumerator to communicate with the deducer in order to steer the deducer in a more promising path. Because the communication process of the enumerator and deducer is concurrent, so we call our framework Densphonia a concurrent synthesis framework. So let's start with some animation. So imagine our original synthesis task as P1. Our solver will try to break this task down using different operators like concat and join. Each operator will try to split the problem into some sub-problems. However, because there are a lot of operators and a lot of different splits, we don't know how to proceed. So we run some enumeration to get this process. So first, it start a single enumerator to help select the most promising deduction. We run the enumerator for a while, and the enumerator find an expression which is T1, and it's shown to be a prefix of P1. And using this expression, we can see that we can deduce P1 using the concat operator. So we run the deduction, and we simplify the problem P1 into the problem P2. And similarly, for problem P2, we can also deduce it with a lot of different operators. And we again take all this possibility to enumerator and try to use enumeration to get some hints. And this time we found another expression which is T2, which is a constant and a substring of both P1 and P2. So based on this hint, it's okay to guess that T2 can be a kind of separator because it's a constant. So because it's separator, we can deduce P1 and P2 using join operator, which is becoming P3 and P4. So our framework will recursively deduce those P3 and P4 until the problem is solved. So let's now illustrate more about this framework on a motivating example. So the deducer starts with the original problem, which is P1. And for example, to deduce this problem, we may use the join operator. So it asks the enumerator to find a constant substring of P1 to split the original problem using join operator. And it may also ask about other operators like concat. So it will be a question like, can I have an expression that produces any prefix of P1? So while sending a lot of those questions to enumerator can handle all of those questions simultaneously. And after some while, it found an interesting expression with its slash. Using this, this expression is a response to the join operator. So when the deducer meets this expression, it further deduces P1 using join operator into P2, which is a list of components from P1. And we can further ask some question from P2, but here we simply ask if P2 can be solved by enumeration alone. And this will be quite hard because P2 need a lot of rearrangement of the inputs. So the enumerator can't find a good solution shortly. So it returns this before that it found, which is guiding to another promising path. So this time it's it's an expression which evaluates to the country code with UK, Australia. And with this expression, P1 is further deduced into P3, which is basically a concat operator, and remove the country code at the beginning. And we continue this process and ask some other further question about prefix. And then we ask, it responds another one, and we ask another one. And just repeat this process. As we can see, it can, Yeah, by repeating this process, we can see it will be finally solved. So then we show the entire architecture of our solver. So our architecture consists a synchronous deducer, which consider each deduction asynchronously with some communication with the enumerator, and a versatile enumerator which kind of multiple requests allows some requests from the deducer simultaneously with a single enumeration. It's also worth noting that to do this, we need a special data structure called term dispatcher. For this part, if interested, you can refer to our paper. So among all those operators, if then else is especially hard to deduce using our method, because the enumeration doesn't really help to deduce this operator. Normally, we want to deduce if then else operator as a decision tree, but what kind of decision tree? If we focus on a small decision tree, it will be pretty hard because it's probably doesn't even exist. You have a lot of terms, and these terms need a lot of deduction enumeration. And if you try to do a larger decision tree, like in the right-hand side, it will be much easier, but it's very likely to be an overfit because you arrange this decision tree out of nothing. It's basically a guessing. So, and the existing approach like EU solver doesn't really handle this problem. So it basically separates term search and condition search, like in this picture, in this figure, and while ignoring the balance of the two. So we want to propose our idea to solve this problem in our setting. So here our approach is basically to use a decision tree learner, which is constantly trying to learn a larger and larger decision tree by constantly increase the size limit. And we also have a worker which constantly generates new terms and conditions and add to a pool for the decision tree learner to learn a new decision tree. So the worker will constantly trying to make a smaller decision tree, but the tree learner will try to learn a larger and larger decision tree. So at some point, these two search will meet in a middle point, and which provide a solution. This solution, as we can imagine, if possible, it will be pretty small, and it will use as much as term and conditions as possible. So actually, the tree learner is actually use basically a linear function to respect to the time to increase the size limit. And for the worker, it's basically, just as I mentioned before, it's a pair of deducer and enumerator. And we also need a pool to share the condition and pool to the condition and solution to learn the decision tree. And let's look at the example for this. So it first ask an example for the worker to ask if it can try to solve this example. And if it's solved, we can use that for decision tree learning. So the worker is responds with T1, which solves not only E1, but also another two examples, which is E3 and E5. And at the same time, we also increase the decision size limit. And at the same time, other worker can also return some conditions and expressions. Like here, it returns C2 C1 in response, which separated E2 from other examples. Because the problem is still not yet solved, it's still impossible to learn the decision tree. So we put another example with the E2, and we obtained T2 in return, which solves this bunch of examples. And because all example is solved by a single term, but it's still impossible to learn the decision tree, so we put two examples into the worker, trying to solve them jointly with a single term, and also trying to find additional conditions to help to split the problem. So actually it got T3 in return, which solves those E2 and E5, but some other example also solved, but it's still not useful to obtain a solution. So we continue to do this, and we obtain another condition C2. With this, it can generate a decision tree. So we put this to a decision tree learner, and we obtain a solution like that. That's basically the idea of our cumulative case splitting to rescue the problem of the balance of solution conditions. So now let's discuss our experimental results. So our implementation is called Symphonia. It consists approximately 7,000 lines of code written in Rust. It's pretty easy to implement with language features like async and await. To access its performance, we'll compare Symphonia against several existing solvers. Yet not all the solvers have the same support for grammar. So for the fair comparison, for those solvers support only standard grammar like if. We compare those solvers with a version we call Symphonia G, which is basically a more limited grammar, which only supports if grammar. And for FlashView++, which have a richer grammar, we use our full solver for comparison. So let's now talk about benchmarks. This pie chart illustrates our benchmarks, which are drawn from 3 main sources. So which is Doit, Harbinge, and Pros, all with their unique characteristics. And we also provide some test case for generality check to ensure the solution doesn't overfit the result. And let's now look at the experimental results. Symphonia significantly outperforms existing solvers in our setting. As shown in figure A, it solves 116 benchmarks uniquely, and in figure B, it solves 531 benchmarks outperforming other solvers, and in figure C, it observed a faster time compared to other solvers. And we also conduct some ablation study with respect to cumulative case splitting, asynchronous deduction, and multi-threading, and it's showing that all of them provide some performance gains to our solver. So that's all for our solver. Thank you. So any questions?
Sorry, the standard usual dump question, did you compare against LLM?
Oh yeah, we compare with it. But at time of this work, we compare to GPT-4o, so we still can beat that one. But with the reasoning model, our method become very weak. So yeah, we will figure out the problem later. Yeah.
Thank you for the great talk. So the accumulative case splitting approach, can it also be used for synchronous setting? So like you can use some sort of round robin method for multiple workers. So.
Oh, what kind of
like you try to solve the overfitting problem.
Yes.
In the accumulative case splitting approach. So can it also be used for synchronous setting? Synchronous setting of using multiple workers, like using round robin approach.
Yeah. Do you mean just do one thread kind of thing, not like multi-threading? Use one worker. Yeah, it works. Like here we have the SP1 version.
B is for that.
Hmm?
The figure B is the case when you use a synchronous setting.
I don't know what exactly you mean by synchronous setting. I mean, if we are talking about just one worker.
No, like I was just thinking of using a single thread, but like there are multiple workers. Like, I mean like.
Oh, okay, I see.
Yeah.
That's probably not benefit too much, I guess, because because you already have. You can simply do a multi-threading, right? If you're doing that, so that's not something our solver considers. So, yeah, but as even proven that even for one thread solver we can beat the FlashView++. So Yeah, we didn't consider that because we have multi-threading.
Thanks for the answer.
Any other question? Okay, let us thank the speaker again.
Okay.
Okay, hello everybody. Yeah, my name's Daniel Riley. This work on exact loop bound analysis is done with Grigory Fedyukovich at Florida State University, where I'm from. All right, so first let me sort of set the stage here with what we're talking about with loop bound analysis. So typically, loop-bound analysis aims to estimate how many iterations a loop in a program will perform. And if you have that estimation, this can be quite useful because you can then extrapolate to get some sort of idea of the cost of a loop in terms of energy, compute, memory, this kind of thing. And most studies are on upper and lower bounds. This has been applied to systems out in the wild and has been useful for program analysis with applications to worst case execution time, scheduling and resource allocation, complexity analysis, termination analysis, and then of course debugging. But we asked the question, what about exact bounds? So, as I said, there's extensive literature on upper and lower bounds. And usually in that literature, if any mention of exact bounds is made, it's in the context of when upper and lower bounds meet, so they're the same. But we thought, well, what if we dial this definition up to 11 and look for more precision for this exactness? So it could be that for any execution of a loop, there's different classes of executions that may have their own bound, and this isn't captured by an upper bound or a lower bound. And what we aim for is that an exact bound should give precisely how many iterations each class of execution of a loop performs. And so we also have the goal in this development that our exact loop bound analysis should be generated statically and automatically. All right, so then let me describe what I mean by this exact loop bound analysis, sort of the high level idea here. So given a single loop program, we want to find a function that computes the exact number of loop iterations based on the input values of a program. So I have a small example here in a C-like program where we have two integer variables that are inputs to the program. We don't know what they are initially. And we have a single loop here that to enter depends on these two variables, both being greater than 0. If we enter the loop, then on each iteration, these variables are decremented. And to give you an idea of what an exact loop bound for this program should look like, it could be something like this, where, again, we're taking in those input values, y and z, from the main program. These are the inputs to the exact bound function. And here you'll see there are three cases for this particular program, this particular loop. One where the exact bound is just y number of iterations, another case where it could be z, And then for this loop, it's possible that you don't enter the loop at all, and so the loop won't iterate, will iterate 0 times. And you see this exact bound captures all 3 of those cases. Okay, so now let me sort of describe the construction of our problem here. So on the right here, I've shown the skeleton view of some augmentations that we make to an input program. So the first thing we do is we add a transition counter. This is a pretty common technique in bound analysis. And we initialize it to some value returned from a function f. Again, so this is like I showed on the last slide, where this function takes in the same input parameters as the main program. So initially, though, f is unknown. Inside the loop, we decrement our transition counter on each iteration. And what we're trying to do is find an f such that when the loop terminates, after the loop, our transition counter has exactly the value 0. So this is the assertion down at the bottom here. We say TC should be exactly 0. This brings a connection to safety verification, where for a good implementation of f, this assertion at the bottom of the program should hold after any execution of the loop. All right, so here's the example I showed earlier, but this time with the augmentations that I just described. We have our transition counter being assigned some value, return value of f that depends on y and z. We have TC, and we have our assertion. So realistically, what this f function should look like, it should be piecewise. Should have a piecewise construction to this function so that we capture all possible cases of the loop execution. The strategy then is to discover each piece of f separately. We want to look for a precondition that narrows down the set of executions that we're examining, and a so-called local bound that applies to that set of executions described by the precondition. All right, so first, although I listed it second, the first thing we do is look for a local bound. What we do is we perform like an angelic execution of the program. So this is just a symbolic execution where we're looking for some good thing, namely that our assertion holds at the end of this execution. We unroll the loop some finite number k times, and we use an SMT solver to get values for the variables in the loop at each step of the unrolling. And then from those values, we guess a local bound. But you'll probably say, well, this guess is not as precise as what you're looking for, and you're right. But we use this, it's good enough to classify a certain set of executions. So just to give you an idea of what this trace could look like, this unrolling that we do, we might start with initial values of y is 2, z is 3, and tc is 2. Then we go through the loop one time and another time and terminate. And we've gathered a set of data here for each step of this unrolling. And it kind of makes sense if you look at it, right? Because we see that TC is 0, which we said should hold after the loop. So we have that here. But we also have that y equals 0. So why does that make sense? Well, as you see, the loop depends on one of y and z being being greater than 0 to enter the loop. We have that. But then to terminate the loop, one of them needs to reach 0. And so this trace captures that behavior as well. All right, so now we need to relate these variables, namely to our transition counter. And a possible local bound for this example is simply that tc equals y initially. So at the top, our function f should return y in this case. But this is only part of the solution. When should f return the initial value of y to initialize tc? So we need to, this is where we get into our precondition synthesis for this particular case. And we use abduction to classify the bound. So again, we perform some sort of bounded unrolling, and then we perform several abduction we perform abduction several times on these unrollings. So for an unrolling of length 1, we'll get this case here where initially y and z are greater than 0, but y equals 1 and z is greater than or equal to 2. We'll perform another unrolling and get another result. Perhaps we can do a third and get another result. And this is great, but it describes only particular cases, namely when we unroll 1, 2, or 3 times. So we need to generalize then on these results to get a precondition for our bound. In this case, we can generalize, the obvious bit is that y and z are greater than 0 initially, but the interesting bit is that for this particular bound to hold, we could find that z is greater than y. And then our transition counter should be assigned the value of y initially. So you and I could look at this and sort of squint our eyes at the program and say, okay, yeah, this looks good, but we want more guarantees than that. We need to verify that this guess at a bound is correct. So we perform another augmentation to our program with this new bit of information. So now we have the original augmented program where we have TC assigned to y this time, and above it we have the assumption, which is the precondition that we found. And then the rest of it is still the same with our assertion that TC equals 0 at the end. Then we send this program with the precondition assumed and TC assigned to y, and we look for an invariant to prove the safety of the augmented program. We can use any external tool for this safety check, and what we find is that this is a good solution. This program, with this restriction here that we restrict the number of states in the program to the ones described by the precondition, and then when we assign TC the value of y, we find that this assertion at the bottom of the program is not violated. So we've found a part of an exact bound for this program, but we're not done. As I said, there are some other cases here for this particular program. So the search continues. And we move to the next iteration of our exact bound search. So what we do is we take the precondition that we found in the first step, and to avoid a redundant search, we negate it and place it as an assumption at the top of our augmented program. Then we go through the steps again. We perform an angelic execution to get some, perform an unrolling to get some new data, guess a new bound, and then look for a precondition on the new bound. So when do we terminate? Well, we perform analysis at each step where we have a precondition and we want to look to see if we need to continue our search. And we terminate when the preconditions that we found do not allow entry into the loop. Here's a little display of the architecture of our exact loop bound analysis. So this just goes through the various steps. We unroll the augmented program. We look for a local bound, which we use an SMT solver. We unroll the original program. We look for a precondition on that unrolling, which also utilizes an SMT solver. We go to check safety and then check coverage. This is the check for the termination of the analysis. If we've explored all of the possible executions of the loop, we report an exact bound. If not, we continue through the analysis. All right, so we've implemented this idea into a fully automatic algorithm in a tool called ALBA. It uses Z3 as the underlying SMT solver. And we've also implemented a sort of in-house data analysis tool to infer our variable relationships. We use Gauss-Jordan elimination and the equation of a line for this analysis. For our invariant generator, our safety checks, we use the tool Freecorn. And of course, we've performed some experiments to check how good this idea actually is. And what we found is that ELBA can find 62 out of 75 single loop benchmarks. We find 62 exact bounds. These benchmarks including in the benchmarks from SVComp, and then others come from termination and bound analysis work. We compared against a few other tools. The upper bound solver Lupus and COAT, and then the termination analysis tool FreeTerm, which finds ranking functions to prove termination. We found that ELBA finds exact bounds on the same order as these other tools come to a result for their own analysis. And then we looked a little further and said, okay, well, so the Lupus and FreeTerm COAT, they're looking for different things, but do they coincidentally come to an exact bound? And on 28 occasions, Lupus did, and FreeTerm came to this result 10 times. But you can see that ELBA is more than twice as good at finding exact bounds on this set of benchmarks. So we think that's pretty good. Our safety checks for ELBA are quite fast in most cases, which is important because we perform several dozen of them at any iteration of our analysis. All right, so to summarize, I've talked about a new approach that we've come up with for exact bound analysis. It's a fully automatic and iterative solution. We generalize from a few inputs to many. We get correctness guarantees on the bounds that we generate from safety checks. We found 62 out of 75 single loop benchmarks on our experiments. And we have several ideas for future work here, which is to extend this approach to multiple loop programs. We want to apply this exact bound technique maybe to upper bound synthesis. Perhaps we can make an advancement here. And then we think that we can also return some information about partial bounds. There could be loops where some executions of the loop are non-terminating and others do have a terminating condition. So we think that we can apply our technique to discover this sort of thing. So that's the talk. Thank you very much for listening.
Any question? Thank you for the nice talk. So the bound function is loop-free or what name of this?
No, the bound function should be loop-free. Yes.
So just if then else.
That's right, yes.
If that's the case, it sounds like you can just take the off-the-shelf cytosolvers, run the loop with randomly corresponding data and collect all the data and then run the cytosolver to generate the if then else expression. Have you ever tried that?
That's not something that we've tried. It's an interesting idea. I guess I'll have to give that some more thought. But the point here is that, well, and I guess I should have mentioned this, that we find that ELBA performs this analysis very quickly, so sub 20 seconds. I would imagine that the approach you're describing could be quite intensive. But yeah, that's something that I would have to maybe give some more thought to. Sure.
Other question? First one on the right. For the first one.
Hi. I was wondering how you would characterize the loops that you used for your evaluation. I guess I am convinced that this can find bounds for these kind of arithmetic loops like you showed. What I'm less convinced about is that you could find bounds for something like a linked list traversal where the iteration count is something like there exists an index into this list such that the item exists and the number of iterations is that index minus the start index. And I feel like I'm just curious if there's anything like that, a kind of data structure traversal that you've got in your evaluation.
No, so you're right. We have limited the scope for the loops that we apply this to. So we haven't gotten to linked lists, arrays, this kind of thing. There are a few conditions that we need. We need determinism in the loop, and that's what we. Yeah, so that's one of the main things is the determinism inside the loop that we need. I didn't talk about it in future work, but this is something that that we're looking into actually. Yeah.
Thank you.
Let us take the last question.
You mentioned at some point use of Gauss-Jordan elimination. Does this mean that all of your inferred bounds are linear in the program variables, or can you infer like nonlinear exact bounds?
Yeah, so yeah, another good question. So right now we're limited to Leah. So yes, linear relationships. We have some work towards nonlinear approaches. Funnily enough, so I mentioned Gauss-Jordan elimination. It's actually Gauss-Jordan's not very useful here. It's this canonical equation of a line relationship that is the most useful technique for finding the bounds for the programs that we analyze. Yeah.
Okay, let us thank the speaker again.
Alrighty, thank you all. I'm Jason, and this is joint work with Michael Ballantyne, Rafi Sana, Will Bird, and Nada Amin. And I'm going to tell you about how to improve the performance of a very flexible kind of synthesis technique by adding staging to relational programming. So this specifically is a technique that Bird, Ballantyne, Rosenblatt, and Might showed off at ICFP 2017. So here we have a function, definition, and use of append, and of course they can evaluate it to its value, but they can also have holes in the call to the program, but actually have the value and produce inputs that would have caused that value to be output. And they can also put holes in any position in the program text, and with some input-output examples, ask their tool to fill in that missing part of the program text. And we should be able to put these holes at any place in the program text or examples, including several places at once, and try and fill in those missing values. And holes anywhere is an important feature of the technique that they're using. And because we can write an evaluator as just a function, then we could implement, say, a regex match evaluator as a function in this and fill in missing parts of the program text there too. So this technique, this trick, is a tower of relational interpreters, or a tower of interpreters with a relational programming language at the bottom. And the downside is that all of those layers of interpretive overhead slow things down. And so this paper, we make it faster by translating staging, a well-known technique from functional programming for removing interpretive overhead to relational programming. So first I need to tell you about relational programming. We want to write relational programs as logical formula, and the execution of the program uses constraint solving plus a complete search to solve for the values of logic variables. If you're familiar with the idea of constraint logic programming, you're in the right headspace. In the paper, the relational programming language we're using is one called minicanron. So for instance, we should want to be able to, for a given triple of terms, inhabit the append relationship when concatenating the first two yields the third. And we want to be able to put holes anywhere in that program, and the relation should be able to query for solutions to the holes that make that true for those triples. So we should be able to answer these kinds of questions. And here, for instance, is a logical specification of append. You can see that the elements of these programs are constraints, equalities over tree structures. We have logical conjunction, disjunction, and they're all used as part of recursive formulae to define relations. Here we have a recursion with a base case and a recursive case. The base case is when the first list is empty, then the relation holds if the second and third are equal. Otherwise, in the recursive case, when the first is non-empty, we introduce some auxiliary variables. In this case, the relation holds when the third element starts with the same thing as the first element, and the rest of the first element on the rest of the second, and the rest of the third are in that relation. So what's neat about this is we're familiar with expressing the semantics of evaluation relationally. It turns out that translating a semantics like this into minicanron syntax is really straightforward, and a bunch of minicanron programmers have done it for some really interesting interpreters. So we should be able to, if we have an evaluator implemented as an inductively defined relation, we should be able to write queries and ask for triples of terms T1, T2, and T3, where the first two are arguments to the append function, and where the whole program evaluates in the interpreter to T3. And we should be able to ask, write that as a query and ask the solver to produce solutions. So the setting so far is we've got this minicanron language. And in that language, we've written a relational interpreter that we can query about ways to use different programs like the append function. And I'm going to use /fun and /rel for function and relation because we've got these multiple levels going on. In fact, we can look at another way to think about defining the append relation as triples for which, when we use the append function in a relational interpreter, the two arguments produce the whole program evaluates in the interpreter to the third. So we can use the append function kind of like though we'd written append as a relation. What's new in this paper is the combination of two components. First is a stage relational programming language, multi-stage minicanron, and the second is an interpreter written in this language that uses staging annotations. So, for instance, in this case, when we have the full text of the append function, then what we're doing is pretty analogous to staging in functional programming. We annotate some parts of the program as things we expect to have at staging time, and some parts that we expect only to have at runtime. And we should be able to specialize the interpreter with respect to the append function. But where it gets interesting is the case where we don't have the full text of the append function. In a synthesis query, this is exactly the situation, right? Where we don't have the full text of the program, that's because we're trying to synthesize part of it. And this is where staging in a relational context starts to feel a little bit different. Because we have this objective of being able to add a hole to any place in the input and still have our staging system take advantage of the known part. And this scenario gives rise to a whole bunch of challenges, including how do you fall back to runtime interpretation at the right places when you don't know in advance where the holes are going to be? How do you stage in the presence of non-determinism? How do you cope with the absence of something like higher-order functions in your language? And how do you stage a program that might be used in multiple different kinds of modes, depending upon what the inputs and what the outputs are expected to be? And for the remainder of this talk, I'm going to focus on the first one, how it is we fall back to interpretation. So why or how is this a problem? Well, if you don't have the full program text at staging time, then you can't have specialized the interpreter with respect to the whole program text. So we can specialize the part that we, with respect to the part that we do have, but what do we do about the rest? Well, our solution, what fills that gap, is an evaluator that's written as a relation that we use at runtime to synthesize expressions. And to focus in, these two programs have to have the same representation of values so that values can flow back and forth across, and control passes back and forth between them. So the append relation needs to use runtime evaluation to synthesize missing pieces, and that evaluator might use the append rel at recursive calls in runtime synthesis. So zoom back out, here's our full picture. The next thing I wanted to point out is that we have two different representations of the same language semantics going on here. The staging time code specialization needs to know about the same language evaluation semantics as the runtime interpretation does. At staging time, we use annotations when detecting holes. So given the part of the append function, we, using staging, produce that append relation. But we also then remove the staging annotations, and that is the interpreter that we use at runtime to do that synthesis. And this erasure property is what makes staged programming special. So these are the specs that we want. This is what we want to achieve. Next, let me tell you a little bit about the actual language that lets us produce the behavior that we want here. In functional staging, we annotate under the assumption that some of the values are definitely available at staging time, and some are definitely only available at runtime. In the context of relational programming, instead, because we're going to assume that you could have a hole in any position in the text, our annotations are either under the expectation that some values may hopefully be available at staging time or may be unknown holes, whereas other values we definitely expect only to have available at runtime. So here's a small interpreter for a language of OR expressions. And there are two different ways that here that we use disjunction. Just the cases are the simple ones, the base cases of true and false, the values are T and F, or we have OR expressions. We evaluate the left-hand expression, and depending upon its value, we either already know the value or we have to do another call to the evaluator. So one of the ways that we use disjunction is for the various cases of the program text. What kind of program do we have? And another is if the first expression in the OR evaluates to true or false. Now that's not about program text, that's about runtime values. So these two different kinds of disjunction lead to two different kinds of non-determinism at staging time. So here, the green part is the part of the program that we'd hope to have at staging time, and the red part is about runtime values that we don't expect to have ahead of time. So for instance, if the computation is non-deterministic because we don't have some of the program text that we wanted, because we don't have enough to decide which branch to take, that's different than when non-determinism happens because of genuine runtime branching based on dynamic data. So instead of a hole in our program text here, we have some variables, x and y, that we want to query for at runtime. And these two different kinds of non-determinism are what lead to two different kinds of staging annotations. And this distinction doesn't come up in the functional staging context. When we encounter a logic variable in what we hope to be static program text, you want to use fallback annotations to defer that whole computation at runtime. You can't specialize on unknown code since there's no meaningful specialization to do. The point is it's a logic variable, it's a whole. We don't have that part. So in that case, the correct choice is to fall back to full relational search at runtime. Whereas when non-determinism arises because of that branching based on dynamic data, you want to explicitly stage each alternative path, generating specialized code for those branches at runtime. True runtime branching involves distinct known alternative code paths. So based upon those two different scenarios, we have two different kinds of annotations. Fallback for the case when you have non-determinism due to an unknown text, and gather when your program is non-deterministic because of non-determinism in the runtime data. So performance. We measured staging time, speed up of staged over unstaged code. If you want the details, read the paper. I deliberately made this so small that you can't see it from there. Don't try, don't hurt your eyes. If you want the breakdown, see the paper. Top line numbers are that we get an average speed up of about 26 times over 21 different benchmarks for different kinds of interpreters, theorem provers, grammar checkers, parsers, regex matchers. And one of the places where we see major improvements is that really neat situation that I mentioned at the beginning, where since eval itself is just a function, we can write an evaluator in the functional language of our relational interpreter, and then put holes in the programs to that other language, and ask our synthesizer to help fill in that missing piece. So you can right now go use this synthesis technique for your language of interest if you write the interpreter in the language of our staged eval interpreter. So go home and try it. The other thing that I wanted to tell you is that if you're doing language parametric synthesis and you're trying to do some ahead of time optimization based on a given sketch of the program, then what you fundamentally have is an interpreter specialization problem. And whereas in order to specialize to that sketch, your specializer needs to understand the semantics of the language. And if you're in that sort of situation, what you should do is you want somehow to get the code that performs these two tasks from one representation of the language semantics. In the paper, we also have the multi-stage mini-canron semantics, the description of the new language forms that we added to mini-canron, comparison with functional staging, and a link to a reusable artifact you can use to go try it out now. Thank you all very much. All right, we can take them offline then. Thank y'all.
Hey everyone, I'm delighted to be here to tell you about our work on program synthesis from partial traces. This work is done in collaboration with my colleagues Victor, Joey, and Daniel at Amazon, and it started while I was a summer intern there. If you've ever used cloud computing for anything, chances are that you've seen a console like this one, where you have some computing instances identified by some IDs, and they show some form of status. And you can use this to perform actions on your instances, such as click a button that says stop instance to stop them from working. What you might not have seen is that under the hood, your cloud computing console may be keeping track of your actions. So when you click buttons in the visual interface, it creates events showing the actions that you took. So let's please consider the following task, where you select some instance in your cloud computing console, and you click a button that says stop instance to stop it. Then after some time, you'll refresh the status of your instance to check if it's already stopped. If it is, you're done, you go home, you're done for the day. But if it's not, you'll go and press a button that now says force stop instance, just to make sure that it's really stopped. Each of these actions will produce an API call that gets recorded by the console. So in this case, when you press stop instance, you will record the very aptly named API stop instances along with its inputs and outputs. Then when you refresh the status, you create a call to describe instance status. And the last call calls again stop instances, now with a parameter force set to true. We can interpret these sequence of API calls as a description, as a trace that represents the task that you were doing. And as you execute this task more times, you get different traces showing the differences in different executions of this task. So as I said, we don't always make that call to force stop instances, so we won't always have the second call to the stop instances API call. If you execute this task very often, maybe every day, maybe even more, after some time you'll have a lot of these traces showing this task that you execute a lot. These traces are already being used by monitoring or billing, so we propose to give them a new purpose. Our goal is to synthesize programs that execute the task represented by these traces. And our end goal is to offer this program to the users to allow them to have a one-click automation of a task that they perform often. The main challenge in this is that these traces of APIs are very incomplete. Although the APIs that are made in the task get recorded, we don't really just want a program that will reproduce these traces. We want to be able to see additional data and control flow to actually produce the user intent and to have a program that will indeed perform the desired task. And even if our traces are very in-depth, there's some computation that only happens in the user's head. So when I said that we'll check the instance status, that is never going to get logged because it's really only happening in the user's head. So today I'm presenting a synthesis framework that we developed for this goal called Siren. Siren takes partial execution traces as the input specification, and by recovering hidden computation, it creates a program that will generalize beyond these traces and actually automate the task the user has performed. And at any time in synthesis, Siren holds a candidate program that is correct. It satisfies our correctness constraint, which is as follows. We consider a program P to be correct with respect to our input traces if for every trace there is an input sigma such that P executed over this sigma will produce that very same trace. Siren starts with an initial program that very intuitively, I hope, satisfies that correctness constraint. So we take the traces and we plug them directly into a cascading if-then-else statement where each branch is just reproducing one of these traces. Then we introduce a variable called branch that works as a dispatcher variable, and it is just describing or selecting which branch gets executed. So recalling our correctness constraint that the program is able to reproduce all traces, hopefully it's pretty intuitive to you that this program satisfies that constraint. If you set branch to 0, you reproduce the first trace, branch to 1, second trace, and so on. Even though that is correct, I hope it's also clear that this is not enough. It doesn't really produce any traces beyond what we've seen, and it for sure does not satisfy the task that I described to you in the beginning. So let's look a little bit under the hood at how Siren will improve this program. So after the initial program, we will go through a series of program rewrites that will improve the program. And some of these will make calls to an example-based synthesizer to uncover hidden functions. The initial program, as I showed, is correct by construction, but it has no uncovered hidden computations, such as the one that happens in the user's head, and it doesn't generalize beyond the traces, so it doesn't really perform the task that we're looking to perform. So the main goal of the rewriting will be to be able to generalize beyond what we've seen in the traces. And this rewriting is basically a search over a library of program optimizing rewrites that we have defined in Siren. Each of these rewrites will maintain the correctness constraints, so the program remains correct, and it will improve the program by lowering a predefined cost metric. Our cost metrics penalize syntactic complexity and incentivize reuse across traces. But if the user would like to improve the program for some other metrics, Siren's method is agnostic to the cost. So some of these rewrites are very compiler-like rewrites that don't really change the semantics of the program, such as noticing that some value gets used a lot of times and hoisting it into a variable that is defined above, or noticing that some of these API calls are showing up in every single branch, so we can again hoist it out of the if-then-else branching structure so that they're in the main body of the program. All of these lower syntactic complexity of the program, thus lowering also our cost metric. More interesting are the rewrites that try to uncover hidden user, well, hidden for us, but user intent. One of these is Siren is able to realize that this whole branching structure that we have here is just defining the value of C1, which is a simple constant. So it makes sense to make C1 instead of a value defined in the program, something that the program takes as input. So we rewrite it as a input parameter. This will lower syntactic complexity as before, and it removes dependency on our branch variable. That doesn't really have a semantic meaning, so this is also something that will lower our cost metric. By doing that, we create a more general program that is now able to perform more actions. Another rewrite will look at the second usage of branch, which is deciding whether or not we make that second call to stop in instances. And the goal here, the question that Siren is asking, is can we infer the user's intention from what we can see? And here we can see a lot more than before, because we have the previous two API calls that now we have access to the data they give as output. So the way Siren finds that out is by replacing this huge of the variable branch with a now undefined function f that takes as input all the parameters available in the program for now. So the output of the two API calls, as well as I1, which we take as a parameter. This will once again lower the syntactic complexity of our program and remove the dependencies on branch and make our program more general. Of course, we still have a problem. This is not a complete program. F remains undefined. So we have these rewrites that allow us to generalize and maintain correctness of our program, but we still have these hidden functions that we need to uncover how they work. And that's where the example-based synthesizer comes in. So we have this function that takes as input everything defined in the program up until now, and then its output is used after its call. The main insight that allows us to find out what to do with this function is that for every trace, we have access to the value of each of the inputs of these functions as well as the output. We see the output to stop instances and describe instance status, which is the inputs to the function, and we can see whether or not we made that second call to stop instances, which is the output of this function. So we can go for every trace and collect the input and output pairs for this now undefined function. And this is exactly what example-based synthesizers take as an input. So we use an off-the-shelf example-based synthesizer to get an implementation for our function, which it can then plug back into our program, having now a complete program. In this case, the implementation will select the third input to F, which is the output to the describe instance status call. And it will compare that output with the string stopped, which is exactly what I told you we were doing in our task. So this is Siren's complete synthesis procedure. We have an initial program that is correct by construction, and we apply a series of rewrites that generalize beyond the traces while maintain correctness. Some of these rewrites also make calls to an example-based synthesizer, which allows us to uncover hidden computation. We initially developed Siren for traces of API calls, but we noticed that we aren't really limited to that. We can work with any trace that is a sequence of function calls along with their inputs and their outputs. And one example is system traces, which your operating system might keep if you're doing for example, some file system manipulation. To show this variety, we evaluate Siren on 54 benchmarks, including cloud automation, file system manipulation, and document editing tasks. We collect these from AWS Cloud Automation scripts, as well as the Blink automation library, and some related work on API discovery. We ran all benchmarks with a 5-minute timeout, and what I'm showing here is a cactus plot, where for each timestamp in the x-axis, it will tell you on the y-axis how many instances were solved under that time. And the running example that I showed you, the stop instances task, takes just under 1 minute to synthesize. Within the 5-minute timeout, we were able to synthesize 72% of our benchmarks. And these will include programs with up to 4 control flow structures, such as conditionals and loops, and up to 2 hidden functions synthesized using the example-based synthesizer. Importantly, all of the benchmarks that Siren synthesizes are correct. We know that this program will be able to generate our traces. For comparison, we tried to run an LLM on the same kind of specification, and we found that it would output the correct program in only 53% of the benchmarks. So I showed you how Siren enriches compiler-like optimizing rewrites with calls to an off-the-shelf example-based synthesizer, which allows it to control data and control flow and synthesize hidden functions, thus producing general-purpose scripts from partial traces of their execution. And I wanted to ask if you can think of other applications, if you work on something that produces these kinds of partial traces with sequences of functions and inputs and outputs, but with some computation missing in the middle. If you do, please let me know either here or at my email. Thank you for listening. I'll take any questions.
Thank you for the interesting talk. I think it's really practical and helpful idea. But if we apply this to a real-world application, how can we determine if the partial traces share the same intent?
That is a great question. In our case, we selected the traces performing the same task. It's not something that we work on Siren, but there is some related work that uses techniques like clustering to select traces that are performing the same task. But as I said, it's not something we've looked into.
But but is the approach robust to some, some outliers which are the partial traces that don't share the same intent?
Not right now, although that is a extension that I am hoping to work on in the very near future.
Okay, thank you.
Thank you.
Thank you for presentation. And I want to ask that what is the average length of your trace and will it influence your performance, synthesis performance?
Length in number of function calls?
Yes.
It's a good question. Do you have an idea? Maybe 10, 15-ish calls, function calls? Around 10. Right. When we introduce loops, these loops will show up unrolled in the traces, so you have the same API call happening a lot of times.
So if you have a longer trace, will you spend more time to synthesize a program?
A longer trace, yes, yes, because in general it means that the program has to be more complex, and the more number of calls that we need to make to the example-based synthesizer, the longer it takes to synthesize.
Okay, thank you.
Thank you.
Hi, Milin Chibi from Uber. Interesting work. Are you assuming that these are sequential programs? How do you deal with anything in traces that's because of non-determinism?
Yes, for now we are assuming they are sequential, and we are not robust to calls happening at the same time or independent calls that may happen in different orders. If that does happen, what might happen is that you have the conditional structure, where in one branch it happens in one order, in the other it happens in the other order. But that is another extension that I hope to be working on in the near future. Thank you.
Thanks for the great talk. A cool application that I can think of right now is maybe trying to try to synthesize an integration test for GUI apps from interacting with the application. So that might be a cool application.
Okay. When you do that, does it create these kinds of traces?
Yeah, I mean if you write an iOS app or like web apps, it's very likely that they have some logging facilities. So we can use those logging facilities to create a general integration test from several traces. So that might be cool.
That sounds very cool. Can you tell me your name so I can find you later?
Okay, I'm Jay Lee. It's just a random thought, so.
Thank you.
Cool.
Thank you. Thank you so much.
Great.
Maybe your last question behind you?
Thank you for the great presentation. And I just noticed that I need this tool because I was a TA of a really big class. It has a 150 students, and I had to set up the VMs for each student, and I spent 3 nights to set all the things up. And my question is that the tool is generalizable to the Python scripts that I use, so I can. It's like there is a script that downloads some packages and install some softwares, and I need to check that it's actually installed and it can be discovered in the environmental variables. So I need those custom operator that is written in my Python script, and I need this synthesizer to do the job I'm supposed to do.
Okay. What would be the logs in this situation? So while you're executing, for one student out of the 150, you are doing this for a VM, right? And do you know what kind of logging that VM is doing?
Like the one typical example is that I have to call the apt-get install. So it's going to it's going to leave some logs in it.
Yeah, that seems like it should work because you have the inputs and the outputs. So in these scripts, from what I understand, they're just basic sequential steps, right?
Basic sequential steps and some checks that if the apt-get fails, do other things. Yeah, you know.
Sounds like, yeah.
Perfect.
Sounds like perfect application. Yeah.
Okay, thank you.
Thank you.
If any of the other speakers are here and want to quickly test your setup, please come to the front. Okay, hello everyone. Hope everyone had a good lunch. I'm Alexa Van Hattem. I'm from Wellesley College, and this is the session on semantics. So up first, we have Nick Ryu from University of Pennsylvania. He is on the job market, so if you're hiring, keep that in mind. And he will be talking about functional meaning for parallel streaming. Go ahead and take it away.
Thank you, Alexa. I'm Nick Ryu. I'm finishing up my PhD at the University of Pennsylvania under Steve Zdansoric, and I'm going to talk about our efforts to design functional languages for deterministic parallelism. So we encounter two problems here that you've probably heard of before. They're very old. The first is that concurrency makes it very easy for non-determinism to seep into our functional programs. And the second is that non-determinism makes programs really hard to write, not to mention debug and reproduce errors. So the classic example is if you have two threads that want to write to the same spot in memory. Well, depending on how the scheduler interleaves these two threads, you might end up with different results. And of course, this isn't limited just to sort of programming with shared state. Many kinds of concurrent models of concurrency suffer from this problem. So with message passing, you end up with races between messages sent by different processes. And in a distributed system, it's 10 times worse. Messages could be reordered, and they could even be duplicated. So what we really want is a language that gives programmers freedom from the scheduler. We don't want them to have to think about how different threads might be interleaved as they write their programs. And that's what determinism would give us. How do we get that? Well, there's been a lot of work in this area. And there's one idea that seeps up and has come up a couple of different times in the literature. And this idea is that if we want to have shared state, we can restrict that shared state. So the data that's stored in the shared memory is some value that's an element of an algebraic semilattice. And the idea is that when you write to that shared state, the value that gets saved in memory is the least upper bound of the old value and the new value that was just written. And the nice thing about this is that it means that it doesn't matter what order your writes are applied in. Least upper bounds are commutative, so you get the same result either way. So lambda join is a functional language that we introduce in this paper that supports a notion of deterministic parallelism using this idea of semilattices and a first-class notion of streaming data. It's highly expressive, so it's an extension of the untyped call-by-value lambda calculus. And we integrate this idea about semilattices by noticing that the lattice theory that's behind these other approaches is very easy to integrate into sort of a domain theoretic framework. And the idea is that that gives us a sort of denotational semantics for a language, and we can go backwards and pull out the language from the math, and the language turns out to have some nice properties. Why do we want another approach? Deterministic parallelism has been studied for a really long time, going back at least to the 70s with Kahn process networks. And there's been a lot of work since then, too. So what's different? Well, we don't think that we have a solution yet that quite meets all of these criteria. First of all, we do want the guarantee of determinism, but we also want a language that's expressive. So it should be Turing complete, and it should support powerful abstractions that functional programming gives us. And it should be one unified language. We'd prefer not to have two different languages, like a sequential language and a parallel language that have to talk to one another. And lambda join is really declarative. So programs very closely match specs in a way that resembles data log. And because lambda join is functional, we get equational reasoning principles, not just over single threads, but actually over entire parallel systems of processes. So let's look at some examples. Here's a really simple example. This is the evens function. It computes the infinite set of all even numbers. Now we're using Haskell notation here, but it's not Haskell, and the semantics are different in a couple ways. In particular, this is a strict language, like I mentioned before. So how does this definition work? Well, first of all, we have the singleton set containing 0 here. We say, well, 0 is an even number. We take that set and we union it with another set. But here, this operator is called join, and it's kind of overloaded. It works as union on sets, but it'll work differently on other types of data like functions or records. And it's not really just a union. It's really this sort of streaming parallel union. The idea is that as you're computing, it runs its arguments in parallel, and as those arguments stream results out, it takes them and it merges them somehow, and then outputs the result in real time. Then on the right hand of the join here, we have a little expression that tells us if a number n is even, well then n plus 2 should also be even. We do that by mapping plus 2 over the recursive call to evens. So here's the function map, which is very easy to define for sets here. We use this big join elimination form. This sort of means take the union of all of the singleton sets f of x for every x in the set x's. And so this gives us what we want. It computes the set of all even numbers. But it's a very strange function coming from the perspective of many other languages, because in most other languages, and including lazy languages like Haskell, this would actually be a meaningless infinite loop. Evens is calling itself back at the same argument. It's not terminating. And in fact, this is an infinite loop, even in lambda join. But lambda join works on a different model of computation. Lambda join programs don't need to terminate to return a result. They can stream them out as they're still running. So lambda join programs are these long-lived computations that stream results out over time. And that means that termination doesn't affect the meaning of programs. It means that a non-terminating program might even be equivalent to a terminating one. As evens runs, it's going to output a bigger and bigger result over time. And this is a property that's true of all computations in the language. They all, in some sense, grow the longer you give them to run. But what does grow mean? Well, it means that they increases according to some partial order. And we call that partial order here the streaming order. For sets, you can think about that order as being the subset order. But for functions or for records, it might be something different, like some kind of pointwise order. And so we have this property that programs grow over time, and it's true of every program. And in order to maintain that, we need an invariant on all of the operations in our system, that they're all sort of monotone over this order. So we can have, for example, set union, but we can't have set complement. And that's a restriction that is pretty familiar in the distributed setting to programmers who use CRDTs, where grow-only sets are like a pretty fundamental data type. So lambda join is strict, like I mentioned before, and it also supports a type of infinite data. And that's weird in and of itself, because usually in functional programming, we use laziness to encode infinite data. And that is not what is going on here. Like I said, this is a strict language. So how do we combine these two ideas? Well, it turns out to work if you have a notion of pipeline parallelism built into the language, right? Or this notion of streaming, that functions are producing output as they receive input. We'll talk more about that when I talk about the semantics down the road. Right now, I want to give you another example, which is a two-phase commit. This is a very basic distributed algorithm. The idea is that you have two peers who are trying to agree on some value, and you have a coordinator that's trying to help them. The coordinator is going to propose some value to the two peers. Each peer will look at the value and decide whether it wants to accept or whether it's going to reject. And then when and if both peers have accepted, the coordinator should commit the result and indicate success. So here's the program. I'm going to explain it bit by bit. The idea here is we are in the streaming setting, right? So the first result that is computed by the system is bottom, and that's just sort of by fiat. Bottom here just indicates a program that has not produced any results yet. The entry point to the system is the system function in the bottom left, and we compute it iteratively. So like I said, in sort of iteration 0, the answer is bottom. But to compute the next iteration, what you have to do is you run the function here. But anytime there's a recursive call, you replace that recursive call with the value of the function that you got from the prior iteration. So the idea here is the last iteration was bottom, so now we're going to be passing bottom to the peers and the coordinator. And then the whole system or all three nodes become bottom. And so in the first iteration, the result is this empty record. In the next iteration, we do the same thing, but now the peers and the coordinator are getting past this empty record. And the peers get a chance to run, right? But the peers accept a record that has some field proposal in them. And so they're not actually able to run yet. The idea is they block until they get an input that they actually want, and empty record doesn't give them enough information to run yet. So they're bottom. But the coordinator does get to run, at least partially. The coordinator runs by producing this singleton record that maps the field proposal to the value 5. And so the state of the whole system now can be seen to be this singleton record, proposal equals 5. And that means that in the next iteration, the peers are now going to see this proposal. So the peers see the proposal, and in this case, they both accept the proposal, and they do that by returning a singleton record mapping OK1 or OK2 to true. And then all of these values, both from the peers and from the coordinator, get combined using join to compute the final result of this system. And so join is going to sort of concatenate these records into one here. And lastly, we have one more step to go, right? The coordinator at this point needs to see the results that came back from the peers. It's going to do that. It's going to look up OK1 and OK2 in the system state. It's going to combine them using logical and then it's going to apply this display result function to compute that to a string. And what we get in the end is that the system has accepted. It has a record field res that is set equal to accepted. So what are we really seeing here? Well, the key idea here is that lambda join makes it really easy to write these iterative fixed point computations. It's very Datalog-esque, but it's sort of dropping a lot of the restrictions of Datalog. We're in a full functional language, can do things like recursion, can work with higher order functions, and all of that. These computations are deterministic, and they're also very naturally parallelized. And they can express basic distributed algorithms like two-phase commit. What else is it good for? Well, even if you're not interested in parallelism or distributed systems, this model of programming can be useful because it gives you a way of dealing with infinite and cyclic data in a purely functional and declarative approach. So you can see the paper for an example of dealing with cyclic graphs. And this could be applied in the future potentially to, for example, static analyses that do iterative fixed point computations, to parsers. And since we handle infinite data and pipeline parallelism, it could even model string processing. Let's look at the semantics. The first way that we give semantics to this language, we give a semantics called an approximate operational semantics. The goal here is to describe how computations evolve over time. But how can this work, right? So the big problem we face is that is this combination of strict data with potentially infinite data. So here we're trying to call this contains function, which asks, is the number 4 in the set of all even numbers? And of course, the answer should be true. 4 is even. And evens is defined correctly. So it should be the case. But because evens is infinite, and this is a call by value language, evens will never run down to a value. And so contains, in theory, might never get to run. So in order to handle problems like this, we need to integrate pipeline parallelism. In other words, we need functions to be able to start evaluating even when they only have a part of their input. Functions need to be able to work with just partial inputs. And the way that we model this in our operational semantics is that a running program might non-deterministically stop at any given time. And if it does that, it just sort of returns a value that is the approximation of its full meaning. And so this sort of is a clairvoyant kind of non-determinism. In this example, you can see that evens stops after it's produced the first 3 results here, 0, 2, and 4. And that's good because that's all contains really needs. Contains doesn't need a full infinite set to produce the correct answer. It just needs to see the part of the input that contains 4. But this leaves us with a few more questions to answer. First of all, I've said that evens represents an infinite set, but how can I even justify that? Right? Operational semantics only tell us what's happened over a finite amount of time. So they can only really produce a finite amount of output. That's not great for infinite terms like evens. And the other downside is, like, in what sense is this deterministic? I started off the talk saying we want to do deterministic parallelism, and then our semantics seems to use non-determinism. Well, the non-determinism is really a trick for getting a cleaner specification. It's not really saying something fundamental about the language. What do we have to prove in order to demonstrate that? Well, you might think that we have to prove some kind of confluence property on a rewriting system, but actually confluence is trivial here. Bottom approximates all terms, so all terms step to bottom. Instead, what we do is we build a denotational semantics. We describe what a program means in the limit as time goes to infinity. That's what the denotational semantics will let us talk about. In order to do that, we use a technique called a filter model. Filter models are basically a way of defining a denotational semantics by defining a type system. We prove a computational adequacy result using a logical relation. And this lets us describe the behavior of terms in the limit as time goes to infinity. And it also lets us define the notion of determinism that we care about, which is that every term has one behavior in the infinite limit. So for people interested in domain theory, there's one kind of interesting tidbit that falls out of this. We solve the domain equation that represents lambda join, and when we do that, we find that sets in this language are denoted using what's called a Hoare power domain. But there's something new here. because sets are eliminated using this big join elimination form that I showed at the beginning of the talk. And it turns out combining these two things, sets denoted by this power domain and sets that are eliminated using this big join form, are surprisingly hard to prove adequate. And so we have a logical relation definition that is tricky and not at all what we expected at the beginning of this project. So take a look if you're interested in that kind of thing. There are a few avenues of future work that we're really interested in. One, we'd really like to be able to support for larger scale distributed systems more than just two-phase commit. And to do that, you really need to be able to handle non-monotone behavior in certain cases. So for example, you might have a key value store that clients can send updates to. And they should be able to update the key value store in arbitrary ways, not just sort of inflationary ones. So luckily, this problem's already been solved in the distributed programming community, and there's languages like Bloom that integrate this really well. And so we talk about in the paper how we can integrate ideas from those languages into this setting. And this is a problem that also needs to be solved if we ever want to be able to support sort of more advanced algorithms like distributed consensus algorithms. We also are really interested in supporting incremental evaluation. When I showed you the two-phase commit example, we sort of reevaluated the whole system at every time step. And you don't really want to do that for real. You want to be able to work with sort of only differences, right? You want to be able to compute the difference in output at each time step. So we think ideas from semi-naive evaluation are useful there. And then we also really want aggregation in this setting, right? So we'd like to be able to express algorithms like PageRank using aggregation, and we'd also like to be able to write distributed quorums where you want to be able to count the votes that are shared between a set of nodes. So in sum, Lambda join integrates ideas from a lot of different areas: functional programming, data log, parallel programming. And if you're interested in any one of these areas, you might be interested in looking at the paper to see what you could learn from the others. Thank you. And I am on the job market, so please feel free to come talk to me. If you have any positions open, my email's on the side. Thanks.
Okay, any questions for the speaker? Do I have student volunteers to run? Looks like there are 2 questions here.
Hi, I'm Jangan Lee from KAIST. First off, thanks for the talk. So as I understand, if you have an infinite computation, but you only need finite time to get the actual answer, then your semantics can find the answer. But what happens if you really need an infinite case? So for example, what happens on contains 3 even in your semantics?
We can't return false, so contains can never return false. It can only sort of return true when the element is in the set, or just essentially block otherwise. And that's a limitation of monotonicity in the language, right? You can't check for the absence of an element in a set. Just like I mentioned, you can't compute complements of a set.
Thank you.
Thank you for great work. It seems like the fixed point computations can be quite long, and it is going to do some redundant computations. So I wonder if you are having some primitives for scheduling so that these computations for this can be somehow efficiently executed without redundancies, or, yeah. So in short, do you have any scheduling constructs to execute this program fast?
So you want some kind of like hints to the scheduler to help it out and tell it what a good schedule would look like? Yeah, I mean, I think the biggest issue in terms of efficiency here is the incremental problem that I mentioned before, is that there's just a lot of repeated computation. And we'd like to be able to do that, to work just sort of with differences over time. We haven't looked at sort of primitives to talk to the scheduler, in particular because we're actually kind of more interested in distributed computation, which is something I thought a little bit more about.
Hi, Max New, University of Michigan. So you did an untyped language. Was that just an arbitrary choice? You could have just as easily done it as a typed language, or is it you need something like data funds type system for lattices and things like that?
Yeah, so the type, you can build a type system, but the type system is kind of non-trivial. The issue here is that typical type systems sort of stop you from not producing any information. Like they stop you from trying to access a field on a record that doesn't exist. But there's a second problem in this language that you might produce too much information. Like you might try to join true with false, and those things have no least upper bound. And so the type system that you would need to prevent that kind of error is different from from most type systems. And so that's still kind of an ongoing research problem. So it's easier to start with an untyped language first.
And you can do that in your language, like false or true?
If you do that in this language, you will get an error. It will be a runtime error.
I see.
And that's the good thing about that is it's deterministic. You will deterministically get an error. But yeah, you definitely want a type system eventually to prevent those kinds of errors.
Okay, thank you.
With that, let's thank the speaker again. And the next talk will be a remote one, so hopefully we can cue that up. And this talk will be on automatically generating optimizations.
Hello, can you hear me?
Yep, we can hear you, and you can go ahead and take it away.
All right, thank you. Hello, everyone. My name is Abdul Rafi Noor, and today I'll be presenting our work titled Misal, Synthesis-Based Automatic Generation of Efficient and Retargetable Semantics-Driven Optimizations. The compiler community has long aimed for greater automation, ideally driven by target ISA and input language semantics, to generate compilers and compiler components. Recent advances in program synthesis, term rewriting systems, auto-tuning, and machine learning frameworks have started to make this possible. These tools and techniques enable compiler writers to express many compilation tasks as optimization problems, enabling high automation. While this is a non-exhaustive list, the point remains that there are many tools and techniques for reasoning about various compiler construction tasks which are being explored in research. Some benefits of why one may want to automate compiler construction tasks are: these are more scalable than human-based approaches, they can identify non-obvious results, they can reason about complex optimization spaces, they tend to be less error-prone, and sometimes even formally verifiable. Finally, these approaches lend themselves to be highly maintainable, such that as the constraints of the compiler changes, these can adapt accordingly. There have been many works which aim to automate various compiler tasks. The tools and techniques are suited for some tasks more than others. In this work, we primarily focus on the problem of instruction selection and superoptimization. There have been many recent works which have addressed this task in different ways and under different constraints. Here, we create a plot with two axes. The vertical axis describes the compilation time when using these tools, which can range anywhere from a few seconds to tens of hours. The horizontal axis describes the size and complexity of the target instruction set. There are tools which support a small subset of operations, all the way to large ISAs with thousands of instructions and in-register data reordering instructions referred to as data swizzling instructions, which are increasingly prevalent in modern instruction sets. As such, we propose Misal. The Misal work is situated in the bottom right corner in this space. We want the performance and flexibility of synthesis-based tools, but to compile in seconds and not hours. Additionally, the compilation should be lightweight so that these tools can be used on a variety of systems. The way we achieve this is by using a semantics-driven approach to scale synthesis, which we'll present in this work. In this context, our contributions are as follows. First, we propose a novel synthesis methodology that enables deriving retargetable rewrite rules automatically by exploiting similarity, but not necessarily equivalence, in the semantics of the target ISA or front-end IR. This affords us scalability both in the sizes of the ISAs which can be considered, as well as the target sequence lengths. Next, we provide systematic support for a special class of modern vector instruction sets, which require reasoning about complex in-register data movements in addition to computational instructions. Finally, we perform additional transformations to generate higher-order abstracted rewrite rules, which fold multiple concrete rewrites into a single higher-order rewrite rule. This significantly reduces the number of rewrite rules which need to be emitted. At a high level, Misal operates in two phases. There is an offline phase to enumerate programs and synthesize rewrite rules on the front-end IR and target ISA. Then, during compilation, a term rewriting system applies these rewrite rules to compile the programs into the target architecture. Simply moving the synthesis offline is not sufficient due to the sizes of the ISAs involved. This makes enumeration infeasible even offline. For example, enumerating x86 expressions to a depth of 2 already exceeds 10 to the power of 12 terms. Targeting rewrite rules with Swizzle instructions requires going even deeper to expression trees with depths of 3 to 4. Then there are challenges with the number of rewrite rules and how to apply these rewrite rules to get good performance. Missal builds on top of our previous program synthesis-based Hydride compiler infrastructure published last year in AS+ of 2024. As with Missal, Hydride operates in two phases. In an offline phase, Hydride consumes ISA pseudocode in vendor-specific format and automatically parses and converts them into a formal semantics which can be used with program synthesis. It also uses these semantics to automatically create a target-agnostic intermediate representation, which folds in many similar instructions across the target ISAs under a unified IR. For example, here are 3 different dot product-like instructions in Qualcomm's Hexagon, x86, and ARM described in their respective vendor-specific pseudocode. These instructions perform similar computations but are not equivalent. Hydride uses these semantics to automatically create a higher-order IR operation for dot product and other operations with additional parameters. We call this generated IR AutoLVM IR. Specific parameterizations of this operation represents each of the dot product instructions shown here. Here we illustrate the compiler construction flow in Missal. It consumes the AutoLVM IR representation synthesized by IR and constructs abstracted rewrite rules on the target ISAs and front-end IR, halide IR in this case, to be applied during compilation. We'll expand upon this diagram shortly. So let's look at the problem of generating rewrite rules offline. Here we show 3 different rewrite rules for x86 dot product instructions with their corresponding halide IR operations. If you see figure A, it shows a 256-bit dot product on 16-bit elements. If you try to discover this rewrite rule using naive enumeration, not only would you have to get the right sequence of operations and correct intermediate vector sizes, you would also have to use the correct variants of operations such as sign extending 16-bit to 32 instead of 8 to 16, for example. This makes enumeration difficult. Coming back to the 3 rewrite rules shown, it just feels like there's a lot of redundancy in this form of enumeration. A and B are doing similar computations on different vector sizes, whereas B and C are doing computations on different vector sizes but doing different forms of accumulation, saturating versus regular. These expressions look similar, but they're not equivalent. We could try to fold in these cases manually, but that would be infeasible due to the sizes of the ISAs involved, and it would be highly error-prone. We approached this enumeration problem by using enumeration with AutoLVM IR. Expression with similar semantics as defined by the AutoLVM IR need to be only enumerated once. If you look at the left-hand side IR and right-hand side IR expressions below, the left-hand side IR captures all 3 of the dot product instructions with the same IR operation, and similarly with the right-hand side IR due to the additional parameterizations. Using the AutoLVM IR representation is beneficial because it is highly compact. If we look at x86 specifically, the AutoLVM IR representation folds over 2,000 instructions into just 136 AutoLVM IR equivalence classes. Enumerating using AutoLVM IR is great, but it leaves us with another problem. How do we know what parameters to use? The answer is program synthesis. To define the synthesis problem, we need to define 2 functions. The first is the abstraction function. The abstraction function takes an expression in terms of the target ISA operations or halide IR and returns its single AutoLVM IR representation with symbolic parameters. Conversely, we have the concretization function, which takes an expression in terms of the AutoLVM IR operation and returns a set of concretely parameterized expressions corresponding to specific target ISA or halide IR operations. As you can see, a single AutoLVM IR expression corresponds to a set of multiple concrete programs. With this in mind, we can now define the left-hand side IR and right-hand side IR to be a valid rewrite rule template if there exists some concretization L of the left-hand side IR and some concretization R of the right-hand side, for which L and R are equivalent. We denote this type of equivalence with the equivalence _IR symbol. This problem can be solved efficiently as a syntax-guided synthesis problem where the syntax is defined using a concretization grammar. This also reduces the number of terms that we need to enumerate with a factor reduction of the cardinalities of the left-hand side IR and right-hand side IR concretization sets. So, the better Hydride is able to fold instructions into the AutoLVM IR, the larger reduction in the number of enumerated terms. Finally, we said that this rewrite rule would be a valid template. We'll show later we can use this template to mine for valid concretizations efficiently as well as separately from this enumeration. Here we show the concretization grammar for the dot product instructions in D. The LHS IR here is the auto-LVM.dot product instruction, and the right-hand side IR is a grammar with the same structure as the above three halide expressions, but with symbolic choices for the variants of the concretizations. Note that even the combination of the leaves is expressed as a symbolic choice, so the synthesis problem also solves for aligning the terminals correctly in the left-hand side and right-hand side. Once we've enumerated using the auto-LVM IR and obtained a set of valid rewrite rule templates, we can mine those templates for valid concretization separately. This is done using the same concretization synthesis problem, but with additional constraints to force either some specific vector sizes or operation variant. Because these concretizations are extracted from the same auto-LVM IR template, we can similarly create an abstracted rewrite rule which represents all of the concretizations using symbolic parameters. For example, A and B on the left-hand side describe concrete rewrite rules on vector addition with 256-bit vectors, which can be done using slicing and concatenation. As you can imagine, this rewrite rule would have many different valid concretizations for different vector sizes. Misal uses program synthesis to replace the numeric parameters with symbolic expressions which fit across the valid concretizations, enabling using a single higher order rewrite rule which represents multiple concrete rewrite rules. Our workflow diagram now is partially expanded to include these steps. Now let's turn to the problem of supporting in-register data movement instructions or swizzles. Generating rewrite rules with swizzles introduces various challenges. To illustrate the complexity, we show that data swizzling required in x86 to target the dot product instruction. There is no single instruction in x86 which does this complex data movement, but rather, simpler data swizzling instructions need to be stitched together to produce a complex swizzle. Trying to directly generate rewrite rules with swizzles and computation is infeasible. As such, prior work with the rewrite rules does not support swizzles. Prior work with synthesis uses various heuristics to support swizzles. These heuristics involve manually analyzing the ISA and creating a complex swizzling instruction, synthesizing in terms of that instruction, and then lowering it separately. This approach makes it feasible to target swizzles but has many drawbacks. First, it requires expert understanding of the ISAs, it's limited to a set of specialized swizzles, there's limited portability for when you want to support a new target architecture, and it's limited to reasoning about a small window of operations. Misal uses a more systematic and automated approach by using the semantics of the ISAs themselves. The existing ISA pseudocode provides a lot of rich information in addition to just the computation semantics. Importantly, we can also analyze the data access patterns in the semantics to automatically create the complex swizzling instructions needed. In this example, we show a simplified version of HVX's widening multiply instruction operating on 4-element vectors. The operands are sign extended in order, but after multiplication, they are written to the upper register in an interleaved manner as shown. So to use this instruction with ordered data, we would need to reorder the vector elements so that the final result after using this instruction is in order. The question, however, is what are these corrective swizzles? There are two possible and equally valid possibilities of these corrective swizzles. First, you could either interleave the operands before doing the sign extension, or you could do a deinterleaving swizzle after the widening multiply, but before the accumulation. Both of these swizzles are derived automatically, and Misal creates specialized swizzling instructions with semantics for both of these variants. Since we have the semantics of these automatically generated swizzles, we can abstract them to the auto-LVM IR as well. The auto-LVM IR of these swizzles themselves are parameterized to support complex swizzling. The added swizzling auto-LVM IR classes do not increase the size of the enumeration set by a lot. The table shows that the number of concrete swizzle Misal finds by analyzing the semantics of the target architectures and the size of the auto-LVM IR. There is a significant reduction in the sizes of the swizzles. This is because of the many variants within the ISAs for different vector register sizes and element bit widths, as well as operations which do different computations but have similar data access patterns. We've now added another step of generating swizzling patterns from the target ISA semantics and abstracting them into the auto-LVM IR. The enumeration and pattern abstraction consequently includes the swizzling operations when generating the abstracted rewrite rules. Enumeration at larger depths becomes infeasible even when using auto-LVM IR. If we wanted to find rewrite rules at larger depths, some form of pruning is necessary, but how? As with the previously described problems, we again turn to the semantics for the rescue. Rather than enumerating all operations with respect to each other, we only want to enumerate operations with each other if they are semantically related. We define semantically related as A is semantically related to B if A can represent either partially or fully the semantics of B. This intuition is nice, but formalizing this has many challenges. For example, the semantics of two operations may be related only if the data are swiveled in a particular layout. The details of these challenges and how Misal addresses these using semantics are described in the paper. After this step, we have possibly overlapping sets of auto-LVM operations to enumerate jointly. The full offline compilation flow in Misal to generate abstracted rewrite rules is shown here with the phases discussed. Then in an online compilation phase, the rewrite rules are used in an equality saturation-based term rewriting system to compile and optimize the Halide application program. We use egglog as our mechanism to apply equality saturation, and the details of which are described in the paper. We evaluate Misal across 3 production target architectures, including x86, HVX, and ARM. These ISAs spans over thousands of instructions, demonstrating the scalability of Misal to real-world ISAs. For comparison, we use the state-of-the-art synthesis-based compiler Hydride, which performs synthesis online, as well as Halide's target-specific backends for said target architectures. Our evaluation covers 33 kernel benchmarks from image processing and deep learning. Finally, we evaluate on the following metrics: performance, compilation time, and memory consumption. With regards to synthesizing rewrite rules, Misal is able to identify tens of thousands of concrete rewrite rules. The rule abstraction mechanism in Misal then successfully reduces these rewrite rules by a factor of around 19x. With regards to performance, Misal also achieves competitive performance with both the manually optimized Halide IR backends as well as the synthesis-based Hydride compilation. This demonstrates that Misal can achieve the performance of synthesis-based tools while addressing key practical challenges such as memory usage and compilation times, which prevents synthesis-based tools from being used in practice. In conclusion, I presented our work Misal. Misal uses a novel synthesis methodology using instruction semantic similarity to scale synthesis. It also performs various analyses on the instruction semantics to generate swiveling instructions automatically, which are essential for modern instruction sets. Misal uses these analyses to synthesize and abstract rewrite rules, which fold multiple concrete rewrite rules into a single higher-order rewrite. The use of semantics to guide compiler construction tasks is becoming an increasingly important area of research, and I look forward to many more works in this area. Thank you for attending my presentation.
All right, thank you to the speaker. Questions? Looks like we have one in the back, and while we get there, I have a quick question. So it seems like there's a trade-off when you're using auto LLVM to kind of collapse instructions into one. Is there a way to expose to the user like how aggressive to be with collapsing instructions, or is that just kind of handled by the system and the user has no way of configuring how aggressive the collapsing is?
So yeah, right now we have, so in the Hydride paper, I think we talk about it a lot in detail. So we have a set of compiler transformations so that we do on the pseudocode to collapse the instructions. And so right now, at least it's kind of fixed. The sequence of transformations are fixed. So the ways the auto LVMIR get extracted are, they're not really exposed to the user, but I think it should be possible to kind of control how aggressively or how loosely you want to fold these classes.
Thanks.
Yeah. Do you hear me? Oh, yeah.
Yes, I can hear you.
Yeah, thank you for the great talk. The framework shows that it takes the input as the pseudocodes of various architectures, and I'm wondering, I'm wondering that where can I get those pseudocode, because it's a pseudocode and there is no real source code out there in the world, and
so all of these, so all of these are publicly available documentation. So for many architecture vendors actually do have some sort of public documentation of their semantics. So all the ISA semantics that we use, they're all available publicly. So Intel has it on, I think, a website called Intel Intrinsic Guide. ARM also has a website for these semantics, and Hexagon has a PDF with these semantics. So we had to write parsers for all of these documentations, but I think architecture vendors tend to provide these documentations to the public.
Okay, thank you.
Thank you.
Hi, thank you for your presentation. And I want to ask if your write rules consider the constants, because I see you abstract away the constants. And in some cases, the rule only valid if you for specific constant.
Yes, we do support rules which are based on constants. So, for example, multiplying by 2 is the same as left shift by 1. So those, then they don't get abstracted in that way. So the constant kind of remains, but basically in the case like that, yeah, it just becomes like the other parameters get abstracted, like the element type or the vector size.
So how do you differentiate these parameters? Like, how do you know this constant is used for vector or something, or how do you know this constant is used for the semantic of this rule?
Yeah, I think we have a different. So it's a bit of an implementation detail which I can talk about offline. But we have a different representation for literals that differentiates between like literals in the parameters and literals as like data.
Oh, I see. Thank you.
All right, let's thank the speaker again.
Thank you.
And up next, we have Matthew Fair talking about introducing verification dialects for MLIR.
Is plugged in. Detecting it. So it was working before. Oh, something happened for like.
He's just detected. It wasn't working. Oh, he just got it again? But no. Okay, got it.
Okay, I'm not touching this. Is this? Okay, I can just. Can I just copy this? Here, take the screen. Okay, well, I'll just. Works. Thanks. Okay, I'll get started. Hi, everyone. I'm Mathieu, and today I'm going to talk about first-class verification dialects for MLIR. But first of all, we need to understand what MLIR is, because not everyone might be familiar with it. So MLIR is not a compiler. MLIR is a compiler framework. It is used to build compilers. And the idea is that in MLIR, you have an IR that is essentially a collection of what's called a dialect, which is an abstraction level in your compiler. And you can extend MLIR with your new dialects, and you can also combine the dialects together in the same program. So if we take like a very simple example of, let's say you have a TensorFlow kernel, you would start with something like a 2D convolution that is in the TF dialect for TensorFlow. You would slowly compile it to a representation that has both arithmetic in it for the add f or adding floating points, but also has an affine for loop that is defined in the IR. Then you would, again, lower this only partly program to the GPU.launch that replaced now the affine for loop. So the idea is that compared to something like LLVM that has a kind of fixed set of a representation, MLIR has these way more complex different abstraction, these dialects, but also can be used, everything can be extended on all of these sub-projects that actually use MLIR. So for instance, there's the circuit project that had those circuit design that use MLIR. There's TensorFlow for machine learning. There's Mojo for general purpose programming language, or there's Hair to do fully homomorphic encryption. And because you have such a big ecosystem of compilers,
there's a lot of tools that you might want to have in your compiler framework. You might want to be able to do translation validation. You might want to do super optimization. You might want to do something that check if your data flow analysis is actually correct or not. But all of that requires one central thing, which is to actually be able to define semantics for whatever abstraction you're defining. And this is what we want to have in this project. So there exist already some tools that can define, let's say, a translation validation tool with MLIR-TV or a bounded model checking tool on circuit with circuit BMC. But the problem is you cannot really use circuit semantics with the translation validation tool that is defined for what I call MLIR core, so kind of the built-in dialects in MLIR. And you cannot use the bounded model checking tool with the MLIR, and you cannot use the bounded model checking tool with the MLIR core dialect as well. So the problem is there's kind of we had kind of siloed semantics that define only some sub-project and are not really exposed for other people to use. And that's kind of the core of this project is, can we make the dialect semantics actually core component of MLIR? Can we expose them so then we can reuse them for other projects? And the idea, as anything is in MLIR, is to just add more dialects. And this time it's called the semantics dialect, let's say, which allow us to represent kind of semantics, and the same way you would, let's say, MLIR would target a CPU abstraction or a GPU abstraction, here you would target a semantic abstraction that would represent the actual meaning of your programs. So we would translate it to our semantics dialects and then use kind of what MLIR always does, which is you progressively lower, like before we went from like a 2D convolution to then affine loops to then GPU launch. Here you would also go slowly up to down to something like SMT-lib, so then you can use SMT solvers for whatever tools you want to use. And the idea is that we can build a lot of tools while reusing everything that we've been defined using the semantics dialect, dialects. All of it is what I want to say is we want to integrate this in part of the kind of MLIR ecosystem by using dialects, transformation as passes, as compilation passes. And we also create that way a separation of concerns, because we have a compiler expert that only has to essentially create a compilation pass from their dialect to the semantics dialect. At the same time, you have an SMT expert that doesn't really have to think in terms of semantics of programs. You just have to think of the semantics of the kind of semantic dialect, the kind of abstraction it has, and how to actually map it efficiently to SMT-lib. And then you have the tool builder that just have to define tools without having to understand the semantics of all possible dialects that he can use with his tools. So let's get a bit on each of these kind of experts and see how this exact like framework would work. So first, the compiler expert. So the way we essentially do mechanized semantics with SMT solvers in compilers in general is you have your program as input, a division by 8. You have a program as output, a shift right by 3, and we just want to do translation validation for it. So what we do is that we compile this, or there's an arrow that isn't really shown. We transform each of these operations into their meaning in SMT. So here division by 8 and a shift by 3, and then we combine them together to a single query that can be passed to an SMT solver. And the thing is, again, if you work with people that use MLIR, the first instinct is, oh, actually, everything is a dialect, so SMT-lib is the dialect. So here we also want to map, the key idea is that whenever we do this translation to SMT, we can just do that inside the MLIR compiler. And that's quite easy because SMT-lib has a simple reference that is based on as expressions, and you just map each constructor to a single instruction in the MLIR compiler, and that's how you define a dialect for MLIR. It's just like very simple. You take each of the constructor in SMT-lib and define an instruction for each of these. So now, if we want to do mechanized semantics through the lowering, through MLIR compilation, which is what we've done, essentially we just called a pass, let's say lower to SMT, that goes from our arif representation to our SMT representation, and that allows us to essentially reuse the MLIR infrastructure to define semantics. And that's really nice because if you can reuse the MLIR infrastructure, that means that you can have compiler experts actually define semantics the same way they would define whatever they do in like the usual work, which is just defining new passes, using the people rewrites that they use in compilers. So that makes them in kind of closer to what their usual environment is. So once we have this, then we can essentially map kind of dialects from their MLIR dialects to an SMT-lib set of dialects. So I separated each SMT theory into its own representation, its own dialect. But the problem is there's sometimes gaps that are too huge. It's how do you translate something like a memref.load, which has to understand undefined behavior, memory, which is quite complex in LLVM. How do we go from a memref, like memory reference representation, to SMT-lib? There's too much big of a gap. So that's why we also introduce kind of a set of high-level semantics that would allow us to essentially simplify the definition of semantics for these dialects, but also, again, as I showed before, creating a better separation for the SMT expert to actually map it themselves to SMT. So the way we can define kind of semantics, this is, let's say, the semantic of writing 42 in memory in some address. And by defining these high-level dialects, you can talk about things like memory effect, where we have here pointers, and then you can do an offset of pointers. You can write in memory, and there's a state that people can use. And you can also talk about undefined behavior effect, like here triggering an undefined behavior whenever you would write in a place that is out of bounds. So this is kind of giving a nice kind of high-level view of a high-level way to define semantics, which is quite nice, so then people don't have to think how it will map to SMT. So now that we have these high-level semantics, we have the SMT expert that can come and say, okay, now it's time to actually map it efficiently to SMT such that the SMT solver will not pass 2 billion years just solving a simple problem. So when we have high-level and SMT-lib semantics, there's two things we want to define. One, which is optimization at each level of abstraction. So there's always things like constant folding and small rewrite rules. And there's also this kind of lowering or compilation paths to go from this memory to SMT-lib. So for that, the good thing is that we don't have to reinvent the wheel. We can just use this wonderful paper about SMT encoding of LLVM memory. And the idea is that we take these IDs and we just have it into our own dialect. So we have the memory effect, that we have some optimization, and then we can lower it to memory, which has this block representation that is defined partly in this paper, and also undefined behavior theory, that we also have passes to optimize them again, and then we lower everything to SMT. And the idea is that we can do this in multiple smaller steps, so it's easier to reason about the correctness of what we're doing, and also to maybe find better optimizations, because we're just looking at very snapshots of, like, we're working at a very specific level in our abstraction. Another kind of things we can do is just have optimization on SMT-lib itself without having to depend on a specific SMT solver. One very simple optimization we can do is whenever we have a function that takes a pair as input, pair as in using the algebraic data types of SMT, we just replace this by a function having two inputs. And when we have a function returning a pair, we would just have two functions that return the two components of the pair. And that seems really simple, but it turns out whenever we did translation validation experiments, we got 60% speed up with Z3, because Z3 would not handle these algebraic data types as much as we thought they would. And we also reduced the number of timeouts we had on our experiments. Note that this did not apply at all to CVC5, which had absolutely no effect whatsoever, because we think that they're actually handling it nicely. So now that we have the semantic dialects, we have a way to map them to SMT, we can actually start building tools around that. So we built 3 tools: a translation validation tool, a pass verification tool that relies on verifying people rewrites, and a data flow verification tool. And the kind of idea on how you would build this tool is that, let's say you start with an arith program, so a program based with the arith dialect, so just simple arithmetic. You compile it using, you apply an optimization pass, let's say just a canonicalization pass, something that do simple people rewrite for optimization. And then we reuse our kind of lowering to, or compilation pass to the semantics dialect. And then we just merge them together, apply some semantics optimization, and we found some bugs in MLIR like this. It's just like a simple way to write a translation validation tool by just reusing the components that we can have. And if we, instead of using arif, we would use something else that has a mapping to semantics, then we can use the exact same tool and it would just work. Another tool we can write is, so the people rewrite verification. So there's the PDL dialect in MLIR, which is kind of a meta dialect to represent rewrites. So we have, for instance, x plus y. So x and y being two operands to value rematching. And we want to rewrite this to y plus x. And it's just like we replace y plus x with x plus y. And so we use a program like this that represents a rewrite. We compile it to the semantics dialect by using the semantics of, let's say, something like arithmetic for the add. And then we apply the semantics optimization, and that way we can kind of verify people rewrites. I'm not going to go much in detail about it, but essentially it's a very simple one-to-one mapping where we have to kind of recursively call a pass in order to give the semantics of things we match and things we rewrite. And we kind of, in the paper, we show that we can essentially prove canonicalization pass both for the comp dialect in circuit and the arithmetic dialects in MLIR proper. And finally, one last thing we do is that we build a tool to do a data flow analysis verification. So we check that the transfer function for a particular operation is correct. For that, we added our own dialects because in MLIR you can always add new dialects when you need them. And we added one to essentially represent non-bits analysis and demanded bits analysis. And we define our own transfer function in MLIR so that then we can use to verify their correctness. So we just take kind of the semantics of a comp program, the semantics of a transfer function, and then we just like kind of combine them to prove their correctness. So in conclusion, we define kind of a set of semantic dialects, not only a single one, that allows for compiler expert to efficiently target target like a semantic meaning, give a semantic meaning of the programs the same way they would target a CPU or a GPU target. And we also define a set of semantic optimization, and we allow people to use the MLIR framework to build their own optimization and efficient lowering to SMTlib. And we have everything that is working in MLIR, so we can reuse the MLIR infrastructure. We build a set of 3 tools that we present in the paper. And this allows essentially a better separation of concerns for everyone involved to essentially be able to define better, define semantics for MLIR, but also use them for nice tooling. And thank you. And if you want to know also more about this, we have an MLIR compiler workshop in September, and part of it is going to be about the semantics. Thanks.
All right, questions for the speaker. Looks like we have one up front here and then one in the back.
Hey, thanks for the great talk. This is Rajat from MIT and Jane Street. I was curious, so the design of the semantic dialects seems tailored to the particular kinds of subdialects from MLIR you have picked. So for example, arith and comb. Comb is just sort of the purely mathematical subset of a circuit that you take. Those seem very nicely able to fit into the SMT dialect. Have you thought about what it would take to embed languages or dialects with more complicated semantics, like data flow semantics or temporal semantics, like the HW dialect in circuit does?
Yes, so for now, everything, so there's, first of all, because we're using MLIR, there's already problems if you use anything that has generic dependent types. That's like something that's quite hard to represent in MLIR itself. Otherwise, we're thinking of things like tensors, which are also quite complicated because it's hard to fit them into SMT. And the idea is that with the way we want to define things, you would have to define kind of over approximation of the semantics. So you would have to say, oh, I know that this thing is commutative, so this is like, we can check for certain properties, but we won't be able to have like exact check that something is correct or not, if that makes sense.
So it's sort of things that fit nicely into SMT are the things
yes.
you will
For now, it has to fit something that you can pass to SMT.
Okay.
Or if we had, if there is like other mathematical language that you can actually have decision procedure, it would be something that fits these decision procedures.
Yeah, thanks for the great talk. I think it's a really great idea to can embed the compiler with the semantic, but I agree that having semantics will help you to build a tool chain, but sometimes there could be no consensus what the semantics should be like. And I think what the people do what people do in this situation is that they only define the portion of the whole semantics. So my question is, do you think it's possible to build some tool chains that only defines the portion of semantics and just leave the other semantics just undefined?
I see, that's interesting. So I'm trying to think, it's kind of this idea of having an over-approximation of semantics, right? Is saying that in these cases, you don't exactly know what happens. And I'm not exactly sure how you could do this, but I'm not exactly sure how exactly it would fit in the system, because if you really say, I don't know what happened, that means it could either be undefined behavior or it could be exactly not undefined behavior. So one thing is, because we represent everything as a pass, you could have one pass for one semantic that people agree on and one pass for another semantic that another group of people agree on. And you can like kind of choose the one you want. So that's one thing that we can do.
Thank you.
Yeah, thanks.
I'm Charit from UIUC. So, so have you thought about like building using existing semantics for stable HLO or HLO like in this?
This is one of the next thing we're looking at least.
Yeah, so there's some existing work on formalizing HLO. Like, did you think about like using that?
So we haven't really looked at it yet, but we should definitely talk then.
Okay.
Okay. Thanks.
All right, let's thank the speaker again. And the next talk will be another remote talk, this one from Toplos on a meta-theoretic reasoning for extensible languages. Go ahead and take it away.
Thank you. I'm Don Michelson, and I'd like to tell you about our Toplos paper, Modular Meta-Theory for Extensible Languages. So in our view, extensible languages are built by combining independently developed components from an open library to make languages. And so by an open library, we mean one where components can be developed and introduced independently of other components and also of other authors. So our underlying assumption here is that combinations of components should just work. The user lists which components they want to use, and then from that list, they get a workable language specification, including the features from all the components. So prior research has shown how this is possible for both syntax and semantics based on modular checks for the components being well-formed. So here, just works means for syntax, creating an LR grammar, and for semantics, creating a full language definition. And so in our work, we extend this approach to meta-theory. So the components can state properties that they expect the combined language to have. Then they can prove those properties modularly, the modular checks for our approach. And then those properties are guaranteed to hold for any combination based on those modular proofs. That's where the just works come into our approach. So before we discuss our modular meta-theory framework, we need to look a little bit more at what our language extensibility framework is that we're proving properties about. So in our language extensibility framework, we have two types of modules, or two types of components. So we have the host language, which is unique in a language library and provides a base of definitions for the library that's shared by all the components. This introduces syntax categories and constructors, as well as semantic relations and rules defining them. Then extensions add new features to the base definitions extending the host language. So they can add new syntax constructors, new rules, and they can also add new syntax categories and new relations, so they can meaningfully participate in defining the language. So then in a combined language, we have all the syntax and all the semantics from the included components, which is the host language plus some number of extensions. And so when we're building a language in this modular fashion, we stick to a principle of how we write the definitions. So if we're defining a particular relation or a particular construct, then that should be defined by the component that introduces the construct or the component that introduces the relation. So these are the two, and it depends on which one knows both of the pieces. And so this makes sure that the language is well defined because it's a component that knows both pieces well enough to give a good definition. but sometimes this isn't possible. So if I write an extension that introduces a relation, you write an extension that introduces a construct, neither of us can define this relation for this construct because neither of us knows both of them. So to get complete definitions, we introduce a notion of projection that we can use to complete the definition. So a projection is a translation towards the host language, getting rid of a top-level extension-introduced constructor that, and instead representing it in terms of some host constructors. So then we can lift our semantic definitions for this relation from the projection back to the original construct. So this gives us complete definitions so that all relations can be defined for all constructs. And so that tells us how our framework works, but why are we interested in a framework like this? So let's look at a simple example. So consider having a host language that introduces some simple expressions, as well as typing and evaluation for them. So then we can have an extension introducing list syntax, as well as typing and evaluation for that. So with the list extension, we can now use the host language syntax as well as list expressions instead of using linked list records. So we get a little bit easier, it's a little easier to write programs. Consider another extension introducing information security. So this gives a static analysis that determines whether an expression is public or private based on the sensitivity level of data stored in the variables that might be used in the expression. So this extension is giving us something new that wasn't in the language before. We can check that private information isn't leaked to public places in evaluation. So this is entirely new. The host language didn't have anything like this. And what's more, with this language framework, in a combined language, we have everything from all three components. So now we can use list expressions in a program while also getting this check that private information doesn't leak. So even though they were written independently, we can use them together in languages from now on. But currently, without meta theory, information security extension isn't really giving us anything because we don't know for sure that its analysis is guaranteeing what it claims. Which brings us to proving meta theory for these extensible languages so we can get the benefits of extension introduced relations as well. So in our meta theory framework, we have two types of properties. Foundational properties, which are introduced by the host language and provide a foundation for the meta theory of the full language, similar to how the host language's definitions provide a base for the definitions of the whole language. So for example, we'd have the host language might introduce a property that its static typing ensures we don't have type errors in evaluation. Then we have auxiliary properties, which are introduced by extensions. So these are auxiliary because they're only relevant when the extension introducing them is included in a combined language. So our information security extension would introduce a property that its sensitivity analysis does guarantee there isn't any private information leakage. And so our key objective here is that we want modular proofs of these properties that are introduced by any component to ensure that they're going to hold for any combined language. And so this guarantee is going to come from creating a complete proof for any combined language based on the modular proofs. So for foundational properties, this isn't too hard because they're known by all the components being introduced by the host language. And so all the components can participate in the proof. So we can orient our proof around case analysis on a relation. Then we get cases for each rule, and each component can prove the cases for the rules that it introduces. So then to create a full proof, we can take each of these, all these cases that are relevant, put them together to get our proof. So the difficulty here is that these proofs often rely on having a complete knowledge of the language due to using case analysis. So the solution is to restrict the proofs so that they apply in any combined language in addition to the single component in which they're written. So things are more difficult for auxiliary properties. We only have one extension that knows the property, so it has to provide the full proof work by itself. But it doesn't know what the other extensions are going to introduce because they're independent of it. So our solution here is to use projections to understand the unknown extensions, similarly to how we use projections to understand unknown extensions for defining relations. This is going to rely on projection constraints. So these are foundational properties that relate the semantics of extension-introduced syntax the semantics of its projection. So for example, we might say the free variables of an expression have to be the same as the free variables of its projection. So these properties specify how similar a term and its projection must be. So then we can use this information to write a generic proof that will apply to proving the property holds for any construct from another extension. So in this case, we know because it's from another extension, the extension introduced relations have to be defined by lifting from the projection. And we know that the projection constraints hold to relate the host language's semantics across the projection. So then the generic proof is going to assume that the property holds for the projection. And then using this information, we're going to prove that we can then lift the property back to the original construct that projected. Excuse me. So then to build a combined proof, we use this generic proof as well as proofs the extension can write directly for rules that it introduces or that the host language introduces. Then the generic proof expands into an actual proof for every case for constructs from other extensions. And then we have all the cases covered, and we have a proof of the property for a combined language. And so once again, as with foundational properties, our modular proofs have to be restricted because we only know part of the language. But overall, these restrictions, while we might expect them to be a little bit restrictive, being restrictions, overall, the cases other than the generic proof are not too difficult to prove. They're much like proving a metatheoretic property without modularity. So the difficulties, when there are difficulties, come in the generic proof, and these arise from the effects that the projection constraints the host language chooses has on what we can prove in extensions. So consider choices between, say, stronger and weaker projection constraints that restrict the semantics extensions can introduce more or less. So contrast a projection constraint saying that evaluation results have to match exactly across projection versus one that says an expression and its projection only have to have the same free variables. In the former case, the semantics introduced by extensions have to be very similar to those that are already present in the host language. Or in the latter case, the extensions can be more different from what the host language introduces. However, it's kind of these affect how we can prove auxiliary properties, because if we know more about extensions with stronger projection constraints, it's much easier to prove auxiliary properties because they're more similar to what we already have in the host language. With weaker projection constraints, it can be more difficult, or sometimes not even possible, to prove auxiliary properties that we might want, because we don't have enough information to even know if the property will hold. It might be that the property will not hold for constructs from other extensions. So the choices that the host language makes affect what properties extensions can introduce, but while those choices do matter, what we want to make sure that you know is that projection constraints do permit us to prove properties from any extension for any combined language based on these modular proofs. And because we can do it for properties from the host language and from any extension, its properties from any component for any combined language hold based on modular proofs. And of course, we aren't the first people who thought about trying to have a modular approach to developing meta theory. Excuse me. So there's kind of two bodies of previous work, depending on the kind of language they're considering. We consider all the previous work to fall short on some of the goals that we have. So the first body of work is for languages that we call complementary components. So these share declarations of syntax categories and relations, but all the syntax constructors and all the rules are introduced in co-equal language fragments. So there's no host language here. So in this kind of framework, there are only shared properties, similar to our foundational properties. And they end up having proof restrictions similar to ours. They don't have a notion of the individual fragments introducing properties. So for languages more like ours, host language and extensions, components building on components, there are a number of works, but there's kind of three categories for the drawbacks that we see with them. So some works say the extensions aren't independently developed. So somebody, the same group of authors develop all the extensions and make sure they work together, and then you can choose a subset of them. Other works do have independent extensions, but if I write an extension and you write an extension, there's no guarantee they're going to work together. Somebody has to put them together, test them, and possibly tweak the definitions to get the proofs to work. And finally, there are some systems where extensions are basically syntactic sugar. They can be developed independently and they're guaranteed to compose, but they can't really significantly contribute to the language. They have to be basically just macros for the host language. So what makes our work unique is that we support open language libraries, meaning we have independently developed extensions, compositional guarantees, and significant extension participation altogether. So, in conclusion, in our paper, we develop a modular meta-theory framework which permits any component in the language to introduce properties. Those properties can be shared as foundational properties, or they can be unique to each component as auxiliary properties. And then we explain a way that you can prove these modularly, either through distributing it to all the components for foundational properties, or having the extension that introduces the property prove it entirely itself for auxiliary properties. The paper also includes a soundness result for our framework, showing that these modular proofs do in fact guarantee that the property is going to hold for any combined language based on being able to take these modular proofs and turn them into a complete proof. Our paper also includes a demonstration of the effectiveness of our framework with a small language proving foundational and auxiliary properties for it. And finally, our paper introduces implementations of both the language framework, which is Sterling for writing the components independently, and Extensibella for writing the modular proofs for them. In addition, Extensibella implements our soundness result, taking the modular proofs and combining them to create an Abella proof, where Abella is a proof assistant, so we're producing machine checkable proofs. And both of these implementations are available at our website. So for future work, we have kind of two threads that are really tied together by needing to exercise our framework more. We have some examples of using our framework, but to test whether it's practical, we really need to have larger examples with more properties that we try out. We also need to have more examples testing the effects of projection constraints. Within even the same language definition, there are many choices that we can have for projection constraints, ranging from very strict to very loose, strong versus weak, and also choosing which semantics to restrict and which not to restrict. So an exploration of both of these will benefit our work in determining whether it's generally applicable and when it's applicable and when it's not. So thank you. We have a link to our paper here, as well as one on the PLDI program. And I'd be happy to take questions now.
Questions for the speaker? I'll start off with one. So early on, you had this assumption that with extensions, they must compose. This kind of assumption that composability must just work. But then later, when you compare it to related work, you say other related work does not provide this composability guarantee. So how are you avoiding sort of circular reasoning and saying we assume they compose, but we also give a guarantee of composability?
So what we're assuming is that they should compose, not that they do. So we're saying in our framework, this is how it should be, and so we need to come up with restrictions and proofs that this is actually going to be the case. So we don't assume that they compose. We restrict things so that we do get the composability.
Cool, thank you. Other questions? All right, one there.
you give us an example that the meta theory of one extension becomes invalid because of the introduction of another extension? And in that case, how do you deal with this conflict?
I'm sorry, I think I missed part of your question. Can you repeat that?
Can you give an example that the meta theory of one extension becomes invalid because of the introduction of another extension? And how do you deal with this conflict?
Yeah, so we prevent this by restricting the proofs that we can write. So when we're writing a proof in a modular fashion, we write it in such a way that it's not going to be invalidated by definitions that are introduced by another extension. So the main way that this happens is in case analysis. So if we have case analysis on something, and in the context of the single component, we have, say, 3 rules that are applicable. Same case analysis in the context of a combined language might have 4 rules that are applicable. So our main restriction on the proofs that prevents adding new extensions from causing the proofs to be invalid in a combined language is restricting case analysis to cases where we know all the proofs, we know all the rules are already known. Other extensions can't introduce new ones. And that's based on our principle for definitions, where only certain components can introduce rules. So I think that answers your question. Please do follow up if it's not clear.
All right, thank you. And with that, we are out of time, so let's thank the speaker again. All right, and our final talk for this session will be on handling the selection monad.
All right. Hello, everyone. I'm Nini Xie from the University of Toronto and Google DeepMind, and this is joint work with my colleague Gordon Potkin at Google DeepMind. I will start the talk with a small program as a motivation. So consider doing binary search that searches an ordered array A for a value x. So the program here takes a value x and the array to search for, as well as the range of the array we will be doing the searching in this case from L to R. And at each step of this function, we are going to pick an index m and compare the element at am with x. If they are equivalent, great, we are done. Or otherwise, if am is smaller than x, then we are going to recursively doing the search for the elements from m plus 1 to R, or otherwise we are going to recursively do the search from for the elements from L to m minus 1. And now the question is, at each step of the function, which m should you choose? Well, of course, we want better m's, because ideally we want as few recursions as possible. And the way we are going to do it is we are going to say that each recursive call is associated with a cost of 1. So you have to pay to recurse. And also, we know that whenever we are choosing this index m, we are going to choose from the range between L and R. And we can also provide some context information, like in this case, the value of x, as well as both values at the ends of the array. So now a clever implementation can take into account, for example, the distribution of the data, as well as the records of past decisions we have made in order to decide better how to select this m. And this example is actually chosen from the Smart Choices APIs developed at Google, which allows programmers to provide choices, context, and feedback to the underlying server, which will perform training and deploy policies for this kind of decision-making problems. In this work, however, we studied decision-making abstractions from a programming language perspective. To summarize our ideas in a single slide, in this work, we combine algebraic effect handlers with a form of continuation that we call loss continuations, which are computational ideas inspired by the selection monad. And we can call the resulting handlers smart handlers because they allow programmers to provide user-defined optimization strategies for decision-making operations, just like the binary search example we have seen in the previous slide. So in the rest of this talk, I will provide some background on algebraic effect handlers before I discuss how they can be combined with loss continuations. To explain the key idea of algebraic effect handlers, we consider an example handler for exceptions. So here, I have an effect for exception which has a single operation raise that takes some exception information and returns a unit. And with this effector signature, we can use this raise operation inside the program. For example, here, we let y be bound to the result of raising e, and then we use this y in this function f. And the semantics of operations is actually given by handlers. So in this case, this handler is going to handle this operation raise. So it's going to receive the argument to this raise operation, and it says that I'm going to do some g using this x. And we can handle this program using this handler. And now when this raise operation is performed, the control of this program is going to be transferred to this handler. And in this case, the handler says that I'm going to evaluate this g with this x substituted by the argument to the operation, in this case, e. And this program is a simplified program, but it already demonstrates the modularity of algebraic effect handlers, which separate the syntax of effective operations from their semantics that are defined by handlers. And in this case, the exception handler aborts the original computation. And one important feature of effect handlers is that it has available the original computation where the operation is performed. So specifically, here we have the same effect and program as before, but when the operation raise is performed, we will also create a continuation that when called will actually resume the original computation. And in this case, the handler is also updated, so it receives not only the argument to the operation, but also a continuation k that's going to resume the original computation when this k is called with some input. And in this case, the handler says, well, I'm going to see whether this exception is a bad exception. If it is, then I'm going to abort the original computation, and instead I'm going to run gx. But otherwise, let's resume the original computation with the value 20. And now our original program will run like this. Well, when this raise operation is performed, the control again is transferred to this handler, and this handler is going to see whether the exception is bad or not. And in this case, we have allocated this continuation k that is bound to where the operation is performed, from where the operation is performed to where this handler is used to handle this operation. And in this case, we also reinstall the original handler so that you can have many exceptions in the rest of your program. And let's assume in this case, the exception is fine. It's an OK exception. So we are going to resume the original computation with 20. And you can see in this case, y is bound to 20. And ultimately, we are going to evaluate f20. And the continuation and the computation can continue. And more interestingly, with effect handlers, because this continuation is available as an argument, the handler can also resume the original computation multiple times. So in this case, I have updated, again, the definition of the handler. So when this exception is a good exception, we are going to resume the original computation twice, once with 20 and again with 40, and then maybe we have a way to choose the better result of these two rounds. So this is called a multi-shot handler. So now the original computation will run, and again, let's assume this exception is a good exception. So we are going to resume the original computation with 20 and 40, and ultimately we are going to evaluate f twice with 20 and 40, and their results are going to be compared according to some best function, and the final results will be returned afterwards. So having seen these examples, we can now define the formal semantics of effect handlers. So here is an example handler language. It's very similar to the core calculi used in most effect handler languages like Coca, Lynx, and other languages. And this is also extremely simplified, but the calculus in our paper supports more advanced types like sum types, product types, lists, natural numbers, floats, etc. So in this case, in the definition of type, we have really just the base type and the tuples and the functions. But the functions that goes from type A to B, the function also needs to keep track of the effect that will be performed when this function is called. And this effect epsilon, it can be either empty or it is some effect epsilon extended with an effect label L. And we have seen the signature of an operation like raise. So it's going to take some argument of type out and then give us back some argument of type in. So in the case of raise, we have seen that raise takes the type of the exception message and gives us a unit. And because this is a simplified language, so we really have just the two forms of expressions. You can either perform an operation, or this operation is going to be handled by a handler. So we can call this op by providing this argument m, or we can evaluate this computation n under this handler h. And in this case, we also support parameterized handlers, which are handlers that can carry a local parameter to it, which is very useful when you would like to implement effectful stateful handlers that can have local states. And the handler is just a list of operation clauses, right? It handles all those operations listed here, and each operation receives the parameter to the handler, the argument to the operation, as well as a continuation k. And this continuation is to receive a potentially updated handler parameter as well as the result of this operation, and it's going to evaluate, in this case, the computation m. And a handler can handle many operations within it, and it also has a return clause that will be applied when the computation returned from the handler without performing operations. So we will not be giving the typing rules for this whole language, but here is the typing rule for handlers. So basically, a handler will need to keep track of the type of its parameter, as well as the computation being handled and the effects that computation can perform, and it gives you back the computation after after it being handled, and also the resulting effect. So you can see L here is gone because we assume the handler is going to handle some specific effect label L. So that's about effect handlers. Now the question is, where are loss continuations, and where do they come into play? Intuitively, we can consider, like, let's say there is an ordinary computation P with type A. So if you run this computation, it's going to give you back a value of type A. Now, a loss-oriented computation is a computation P that receives a selection function from A to real and then gives you back a real. So you can consider this real as that cost number we have seen before, or the loss that is associated to every choice of A. So this P says, if you can give me a selection function that tells me what kind of loss is associated to each choice of A, I'm going to give you back an A according to the selection function. So maybe this P will say, I'm going to return the A that maximizes the loss, or I'm going to return A that minimizes the loss, or it has some its own criteria for selecting this element A. And because we have this element A available and we have the selection function, so we can also return the tuple that has both the loss value as well as the element A. And if we look at the type signature of this loss-oriented computation, it looks very similar to what people call the selection monad in the literature. So the selection monad of X is basically something of this type. It also takes a function from X to R, where R is the real number, and it gives back an X. So if we generalize the type a little bit, we can also say the selection monad has type from X to Y to X. So then people who are familiar with continuation monad may notice the similarity and the differences between continuation monad and the selection monad, where continuation monad goes from X to Y, and the selection monad goes from X to Y to X. And similarly, we can combine the selection monad with the loss monad and then return both tuples. And with that, we can now start incorporating selection monad into effect handlers. And the way we are going to do it is that we are going to adding one language primitive, and then we are also going to update the definition of the handler. So specifically, we have the same definition of types and effective signatures as before, but now we have one additional language construct that's called loss. So we can call this loss with a term m. So that is telling that the program that I'm currently incurring a loss of term m. And now the handler is also updated. So in addition to the handler parameter and the argument to the operation and the ordinary delimiting continuation that we have seen before, it receives the additional continuation, which is a form of loss continuation that we call the choice continuation. So it's similar to the continuation that we've seen before in the sense that it receives the output of the operation. But different from the continuation that returns something of type B, this choice continuation returns a loss value, which is basically the cost or the loss value associated with each choice of the operation output. Now this handler can make use of this loss continuation, and this allows programmers to write handlers that handle operations according to this loss information and maybe resume the original computation with a particular selection of the operation result. So let's see some examples to demonstrate how things work. As a very simple example, we can look at a minimizer handler. So in this case, here the program password tries to choose the password from a list of candidates. So it calls this effector operation pick, and it provides a list of candidates. And whatever candidate is chosen, this program says there is specific loss associated with your choice of the password. Because maybe I want the password to be as long as possible. So there is this loss of the negative of the length of the password. And maybe also I want as many distinct elements in the password as possible. And after that, I'm going to return the passport that you have actually chosen. So this program is not responsible for choosing the ultimate password, but it knows that whatever password you choose, there is going to be associated loss. And now you can write a handler that actually does this password choosing, and this handler determines the choice using this loss continuation. And in this case, it's a minimizer handler, so it says, because I have a loss continuation available, I'm going to call some function minwidth that's going to select from the list of the candidates the element that minimizes the loss. And after I'm done with the decision, I know that I have chosen P as a password, and I can resume the original computation with the password I have chosen. So in this case, we are going to probably return AABB or ABC because they are both longer and have more numbers of distinct elements. And this program gives an example of what we can do with the loss continuation. And since we have this loss continuation available, we can also do more advanced things with it. For example, we can do linear regression. So this is an example that corresponds to one iteration of the training program for linear regression. And at each iteration, we are going to make a choice of the weight and bias that is used in this linear function. And we are receiving input data and then the expected output data. And at each iteration, we are going to apply this linear function to predict this y prime. But of course, this y prime can be different from the actual y we want. So there is some loss that occurs because of the difference between these two values. And afterwards, we are going to return the updated weight and bias. And now, the handler can determine the choice of the new weight and the bias using automatic differentiation. So in this case, the handler will apply the automatic differentiation to this loss continuation and gets the gradients of the weight and the bias, and then do one step of gradient descent so that it can update the weight and the bias, and then it can continue the original computation with updated weight and bias. So I hope this gives you an intuition of how loss continuations are combined into effect handlers and how we can make use of them to make decisions by defining optimization strategies as handlers. So I probably won't have time to go through the formal development of the calculus. We have the operational semantics in the paper, as well as lots of the operational semantics rules. And we have meta theory developed. So we have proved our operational semantics preserves type, is deterministic, progresses, and also under some assumption that effect handlers are well founded, we proved that our calculus is terminating. And there are more things that you can find in the paper. We also have fully developed denotational semantics that is proven to be sound, and we proved adequacy result that the denotational semantics coincides with operational semantics. And we have implemented our calculus as a Haskell library and provided more examples in the paper, including two-player games, hyperparameter tuning, and Nash equilibrium. With that, I'm happy to take questions.
Questions for the speaker? One up here in the front.
When you work with your selection monad, did it occur to you whether you should have titled your paper and oriented your work and called it handling the continuation monad instead of handling the selection monad? In other words, if you had just tackled the continuation monad, what would have been different and what would have stayed the same?
So it's a question that if we change the selection monad to the continuation monad, then what would happen? So that's a very interesting question. So with continuation monad, what you care is about the result of the final program. But with the selection monad, what you care is the input to the continuation. And this is, I think, the key for lots of decision-making process, because you don't care about the final value, but you care about the thing that, the choice that you have made in this process. So for example, if you take linear regression as an example, right? You don't really care about the final loss that is produced, but you care the weight and the bias that is produced in the end. So this is the part about the selection monad. So if you instead use continuation monad, I cannot imagine what the semantics will look like, but it's very likely that you will lose the information about the thing that you actually care about, which is the selection of the weight and bias in this case.
Take that offline since we're just about out of time, and let's do one brief question here if you have a brief question.
Yeah, sure. So on the same slide, the loss continuation L, does that also come from continuing with computation where you left off? Is that how that works?
Yes, so the choice continuation ultimately is a combination of the delimited continuation and the loss continuation in the context. So basically, it takes the result of the program and also applies it to the current loss continuation that will actually calculate the loss of the whole program.
Cool.
Great, and with that, we are over time, so let's thank the speaker again.
Thank you.
And a reminder, there is a break and special treat for students, so enjoy that, students. Thanks, everyone.
starting of 6th, you start writing, but end of 6th is usually.
Yep. Are you presenting someone?
Yeah. Wait.
Wow.
I'm going to say something.
Oh, right. Yeah, okay.
Very much for that.
Hello everyone, I'm Charit from UIUC and welcome to the HPC session. And today we have 4 talks in this session. And first of all, Rohan Yadav from Stanford is going to give the first talk about task-based tensor computations on modern GPUs. So Rohan is a 5th-year PhD student at Stanford working with Alex Icahn and Fred Kohlschlag. He is also a part-time researcher at NVIDIA working with Michael Bohr and Michael Garland. And most importantly, he'll be in the job market next year. So with that, Rohan, you can take.
Okay, thanks for the introduction, Charit. Hold on, let me start my timer, make sure I'm on time. Okay, so hey everyone, I'll be telling you today about a different way of writing tensor computations on the crazy GPUs that we at NVIDIA have been building. So, well, if you look at GPUs over the past couple of years, despite the end of Moore's law, we have these beautiful marketing diagrams that show performance continuing to go up, despite our cores not actually going that much faster. And the main reason for this is, one of the reasons is due to specialization, in particular the introduction of tensor cores, which started back in 2016 in the Pascal era GPUs. So what is a tensor core? Well, a tensor core is all it is just a little instruction that the GPU provides to do certain kinds of matrix math faster. So on the Pascal architecture, this started off really small, where a single thread could say, hey, I want to do a 4x4 vector dot product, and you would get that done for you a little faster than the normal set of instructions. This became a bit more complicated in the Volta architecture, where you actually had a matrix product now, so you could do an 8x8x4 matrix multiply. But the caveat was that now you had to have 8 threads cooperate to do this multiplication. So your inputs and output would have to be sharded across all of those 8 threads. Again, this became a little more complicated in Ampere, where you now are doing a 16x16x8 multiply. But the complexity increased too, where now 32 threads had to share the inputs and outputs of this multiplier. This has reached a crazy inflection point in the Hopper GPU, where you have a humongous tile size, in particular 64x256x16, and now 128 threads have to all cooperate to use this beast of a tensor core. And this thing is so big and fast now that NVIDIA had to add a data movement accelerator called the TMA to make sure data could move fast enough to actually feed this tensor core. So I showed you a scary picture here, but what does this actually mean for the kinds of programs we want to write? Well, I'm going to argue that this is fundamentally changing the CUDA programming model. So I've shown up here some code that you would use to write a gem-like computation for GPUs before Hopper. This looks something like a classic Atlas-style BLAS, where you're decomposing your computation into tiles, and then it was written in a very bulk synchronous way. You don't have big accelerators, so all your threads have to cooperate in loading some data from global to shared memory, loading some data from shared memory to the registers, and then actually doing a gem. And the thing that was good about this was that your compiler and your hardware did a lot for you to actually overlap all of these stages. The hardware would make sure that all these loads were happening on different units, and then the math was happening separately from those from the loads. In Hopper, this has changed a lot. In particular, now that we have all these big accelerators that do a lot of stuff for us, we get something that looks much more like task parallel code from this bulk synchronous stuff from before. So in particular, your code now has to be warp specialized, meaning that some threads are going to be responsible for invoking this asynchronous data mover called the TMA, and then a separate group of threads will be responsible for actually invoking this tensor core. these things are going to communicate through basically shared memory barrier objects, kind of poking each other to wake up and go to sleep back and forth. And then these accelerators themselves are now asynchronous, meaning that you invoke them and they return immediately. But then to actually check when it's done, you have to start polling some flag in the background that tells you when this copy is done or when this matrix multiply is done. And even more annoyingly, the tensor core is a separate processor on the chip now, so then you need to actually find work to do to fill your normal floating point units while the tensor core is running. And so in some ways, this whole software pipeline of writing a gem has gotten easier because the architecture became more complicated. But at the same time, the difficulty switched, where now we have to write this task parallel asynchronous code, and humans have been historically terrible at doing this. We are not able to write code like this very well. So I think our programming systems, like we at PLDI, need to evolve to face these kind of challenges. And I think there's several trends that are all colliding that make me very scared as a programming languages researcher. So first, there's this proliferation of these on-chip accelerators. Kind of we have this data mover, we have these matrix multipliers. And so as the set of things we think are important continue to change, we're going to get more and more of these accelerators. And then there's going to be this difference where every time we add some more accelerators to our chip, we have to keep changing the code we write. Like I showed you, the code was so different between before Hopper and after Hopper. Then there's this pervasive asynchronous programming that is starting to hit our programming systems, where everything is asynchronous as these hardware units get bigger and bigger, and they require really deep pipelines to keep them fed. And so this code has to be both high performance and asynchronous, something that is hard. It has to be correct and fast. And getting both of these things at the same time is known to be quite difficult. The real nail in the coffin, though, is that everybody wants to write their own programs for these devices. We can't just hide behind BLOS anymore, because everyone wants to write a custom kernel for their custom neural network. And so we have this that we have more code, it's getting harder to write, it's changing over generations, it's asynchronous, and has to be really, really high performance. So this is a very scary combination of things. So what we wanted to do in this work was to provide automation for a lot of these low-level, difficult things to do, but instead leave a lot of control for people who know what they're doing to get high performance. And so what I want to give to the programmer is a programming model that has sequential semantics, meaning that I want to automate away things like dependence analysis, data movement, synchronization, and concurrency. But I think it's really important to retain explicit control over things like how your data is partitioned amongst your GPU. Where does the data live in the GPU memory hierarchy? And the ability to exploit architecture-specific capabilities. If you look at the programming systems that we have today, you kind of get one or two of these things. If you have systems like Cutlass or Thunder Kittens, basically they don't really do that much for you to help out with these difficult parts of writing the code, but you are able to write that beautiful sequence of instructions that gets 100% of peak on the machine. So you can get that high performance, but you don't get too much help to make sure your code is actually correct. Or you have systems like OpenAI Triton or the recently released CUDA Tile, where you get a very nice sequential-looking programming model. These tile-based models are great, but you don't get to control these other things at the bottom. In particular, your compiler has a bunch of heuristics to decide what to do here. And I'll show you there are many cases where your compiler does not do the right thing, and you as a programmer have no way to tell the compiler what you know and want to do in your program. So in this talk, I'll talk about one way that we can get both of these things, and by picking what I think are good abstractions, we can get both automation of difficult things and get really high performance code. So I'm going to talk to you today about a system that we built called Cypress. And so Cypress, you write programs in Cypress, they have two components. The first is a logical description of the computation, which is a task-based parallel program with sequential semantics. Then you write separately a mapping description of the program, and this is going to specify a variety of performance-sensitive decisions that you actually will bind your program onto this physical machine. So I'm going to talk mostly in this talk about Cypress programs, and if you want to see about our compiler, you can go check out the paper. Okay, so let's talk about what machines look like and how we model them, because that will motivate the kind of programs we want to write. So the GPU is a very hierarchical machine, and we're going to model this pretty directly with the hierarchical structure of the processors, where you have processors that describe different levels of this machine, such as the host that actually launches GPU kernels, blocks that run on SMs, warp groups, warps, and threads. And then you have different memories, like the global memory, which every processor can access, the shared memory, which is visible to only one SM, or the registers, visible to individual threads. So you have this hierarchical machine, and basically we're going to write programs that decompose both our data and our computation across the processors and memories of this system. Okay, so here's a little component of a Cypress program that computes a gem. And so I'm going to first just explain the syntactic structures in this piece of code, and then we'll put them together to kind of interpret the program. So a Cypress program is written as a collection of tasks. So this is the gem task. And you can write, and every task has a set of variants. You can think of a variant as a concrete implementation of a task specified for a particular level of the machine hierarchy or for a particular algorithm. These task variants can either be inner or leaf variants. This particular task is an inner variant, and so inner variants get to launch more tasks. They get to decompose their data and decompose the computation, for more recursive structure. They can do this in a few ways. One of them is with this p-range operator, which is going to launch a parallel group of tasks that don't interact with each other, or the s-range operator, which is going to launch a group of tasks that must execute one after the other. We have leaf tasks, which you're not actually going to see in this talk, but they're actually going to execute concrete computations, like launch some work onto the tensor core or do some floating point math. When we talk about data, every task is going to take in a set of tensors, and then they're going to describe to the compiler how they actually use those tensors. So for this gem program, this gem is going to read the input tensors A and B, and then write to the output matrix C. Finally, tasks get to partition their data through a series of structured partitioning operators, such as this blocks operator, which is going to break up tensors into tiles of the given shape. So putting it together, what does this program do? Well, at the host level of my gem, what I want to do is I want to break up my matrix, my output matrix into tiles, construct panels of A and B that each tile needs, and then launch a bunch of parallel work, where each subtask is going to compute one of those output tiles of C. So let's look at a different algorithm, a different variant that you might choose for a different level of your machine hierarchy. This is the block level variant. So now running on an SM, you have shared memory and registers to exploit, so some locality to use. So for this particular algorithm, I'm going to use a different choice, where instead I'm going to create an accumulator tensor, and I'm going to break up my k dimension of the iteration space into chunks. And then what I'm going to do is I'm going to initialize my accumulator. I'm going to then loop over the k dimension in pieces, launching gems that accumulate into my accumulator. And then finally, I will copy that accumulator back out into the output tensor. And I want to emphasize here, I've shown you two task variants, and note that this code is sequential. There's no explicit data movement, there's no concurrency. All of it is going to be done by the compiler, and here we're just structuring a program that says, here's the logical algorithm I want to run. Okay, so let's talk about then binding this program onto a real machine. So the mapping description is where we're going to encode a lot of performance-sensitive decisions. We can do things like say at a particular task call site, what variant should run? What processor should that task run on? What memories should it put all its tensors into? Then we can also specify a variety of tunable decisions, kind of hooks into the compiler. Things like, what block sizes to use, how deep should you software pipeline this loop, and so on. So concretely, you can say things like, I want this task in the task hierarchy to put its tensors in shared memory, and these tasks lower to put their data into the registers. And the compiler is responsible for moving the data and maintaining synchronization as these mapping decisions change the program. So the Cypress compiler is going to take these two things in and output you some code in the cute C++ library that actually runs on your GPU. And it has got a bunch of passes that you can check out our paper for more details. But at a high level, these passes are going to lower away tasking abstractions, and then they're going to perform optimizations to actually bring that code closer to what expert would write. So the first result I want to show you is that first, our compiler infrastructure can lower these Cypress programs into high-performance code. So for important computations, like gem or batch gem, we can get code that is very competitive with cuBLAS. That's kind of expected because we know exactly, these systems are built by the expert engineers, and we know the decisions that went into making those high performance. A more interesting part is that when you're trying to compare against high-level systems, the control that Cypress gives you enables you to do better than these high-level systems when their heuristics fail. So for computations like this dual gem, you're fusing two unrelated matrix multiplies together, or this gem plus reduction computation, where you're going to while you're doing a gem, you're kind of performing a streaming reduction on one of the other tensors, being able to control things like, hey, I want to put the reduction output in the registers rather than in the shared memory, which Triton does, can be the result of a significant performance difference on this machine. And so, you really there's a lot of benefit to turning the compiler inside out and being able to give these decisions as you know them rather than having it figured out for you. I think the most interesting program we've written in Cypress is Flash Attention 3. And so if you don't know about Flash Attention 3, I don't want you to actually read this code right now, but the basic idea of Flash Attention 3 is that it was an implementation of this key flash attention algorithm for the Hopper GPU. So they kind of had to redo a ton of stuff in the algorithm to perform well on Hopper taking advantage of all of these asynchronous features of the architecture. And so if you look at this code, there's a ton of stuff that I don't like here. Things like wait for this thing to be loaded in shared memory. Launch this WGMMA, but commit it and don't wait. Launch this thing, but do wait. And in fact, if you look at all this code, it is more than the actual algorithm of flash attention. And I want to make the case that if you program in a language like Cypress, where we take seriously our compilers should not have make people deal with this, like all of this code goes away, and you write something that looks more like the actual math you want to do. And I want to also emphasize kind of a more to call to action. The main thing that Flash Attention 3 does, if you know about it from Flash Attention 2, is a software pipelining transform on the main loop. And kind of if our compilers were better, we could have done that automatically rather than waiting for 3 years architecture to come out and get it. Like, we should have been able to do that by ourselves. Okay, so coming back to the main point, we can automate all of that data movement and synchronization, but still get code that compares well with the handwritten flash attention algorithms. So with that, I'm going to conclude and leave you with a few thoughts that I really believe, especially from my background in actually writing distributed programming systems, that things like communication and synchronization should be the language implementation's problem. Like, these are hard things for people to get right, and our compilers have a lot of knowledge of how to deal with that things. And so I showed you today a set of abstractions, particularly task-based abstractions, that are one way that we could actually make this a reality. And I showed you how we can use them to express high-performance tensor core computations and run efficiently on modern GPUs. With that, I'll conclude, and I'm happy to take any questions. Find me offline. Love to talk about tensor cores.
I have one question. Like, so you implemented flash attention, right? So flash attention has this kind of softmax accumulation that is not correct in the intermediate stages, but finally it cancels off, right?
Mm-hmm.
So how did you implement that, like, specifically?
Well, I mean, we have the difference in our programming system. We're not starting from like a really high level algorithmic description. We're starting from a description where you say, here are the tasks I want to run. And so those tasks are allowed to do, those tasks are written in a way that say, I want to do the softmax reduction and just put the data here. Like, we're not leveraging semantics of the linear algebra. We're just leveraging semantics of saying, this task will read to some data, this task will write to some data. Therefore, these tasks need to run in a certain order. So we could just, we write down the flash attention, but we kind of copy this algorithm description into the code. And so we don't recover that accumulation, we just do what it said to do.
Yeah, I had one more question. Like, in the results, like, there were like few slowdowns. Like, could you explain like what were the reasons for those?
Yeah. So this particular, I mean, the main reasons where we're a bit slower in the flash attention algorithm is we don't yet implement this particular optimization called the persistent kernel optimization, where you have where basically you launch a fixed number of thread blocks, and those thread blocks sort of grab work that they want to schedule. So you basically, at small problem sizes, you avoid certain overheads in setting up and tearing down CUDA kernels. You could presumably do that in our model, like a p-range loop over your blocks doesn't have to turn into a thread block with that same width that could be implemented by a set of blocks that are scheduling themselves. Yeah.
Hi, this is Son from NYU. So I personally don't have a lot of knowledge about these compilers for GPUs, but if I remember correctly, Thunder Kittens was one that allowed you a lot of low-level kind of control over things, but didn't give you these nice abstractions. And yet, it seems like Cypress outperforms in some cases, like in longer sequence lengths, even Thunder Kitten. So can I ask, where do these extra performance benefits of Cypress come in? Like, how is it able to do even better despite being higher level?
Yeah, so first, I mean, one thing is that Thunder Kittens, at the time of writing, Thunder Kittens, they had only implemented Flash Engine 2 in their things. So there's a slight algorithmic difference. You'll know that actually you can like reconfigure the system. You can kind of reconfigure these algorithms to actually perform very similar to Flash Engine 3, which is a separate thing. But there are a lot of small differences, I think, inside the actual just generated code. Like, we're at the level that individual cycles tend to matter. And so they wrote their own infrastructure for interacting with the tensor cores. I was reusing stuff that NVIDIA built. I mean, you can imagine there are small differences in that exact generated code there. I think fundamentally, if you at the high level C++ code that's generated, they're mostly the same. And I actually, I looked a lot at those blog posts. They're very good to help me learn about the space. Yeah.
Quick question. All right. If not, let's thank the speaker again.
Oh, yes.
Next, we have a special speaker, who is actually my PhD thesis advisor. So Professor Saman Amar Singh is going to speak next on lightweight and locality-aware composition of black box subroutines.
It's kind of intimidating to first go after my academic grandchild, because it's a Fred student, introducing me by, hopefully I did good, he didn't say anything bad about me, so. So today I'm going to give this talk on behalf of, Okay, this is work done by Manya Bansal. Unfortunately, she couldn't be here, and all my co-authors also decided not to come, so I got unanimously elected to give this talk. So I'm going to talk to you about lightweight, locality-aware composition of black box subroutines, a build system we call FERN. So let's start by looking at how do matrix multiply. You want to do very high performance matrix multiply. You can, if you want, go write these 5 lines of code. This is something even undergrad can do easily. The problem is, if you write these 5 lines of code, you get matrix multiply. It runs really, really slow. The fastest matrix multiply you can get in a library is, in this case, for large matrix size, it was 600 times faster. So the reason it's 600 times faster is this fast matrix multiply has been written with hardware in mind. A lot of work has been done to make sure that matrix multiplier really fit into that hardware. First of all, it's tiled, so the data that you bring in will stay in cache and use multiple times as much as possible. It's vectorized, so vectorized gives you most amount of flops, so you get the maximum flops out of a processor. Obviously, modern processors have multiple cores, and you might even have multiple chips, so you want to parallelize it to get the best performance out of that. You might even want to do cache blocking, so the instruction cache doesn't overflow, everything fits in the cache. And if there are any pipeline stalls, you might want to reorder the instructions in a way that there's not going to be any pipeline stalls, so you can get software pipeline. This is great, and this is not that easy to do. I don't know whether Vikram will agree, but something like LLVM compiler is not able to get this kind of performance today. They will do a good job, but not at the level that completely utilizing everything available in modern hardware. And on top of that, the hardware also keeps changing. If you want to get there, you can get a domain-specific compiler for very tiny domain that will only work with certain very specific class of functions, and they are for certain architectures that will do really well. If you really want to do it, basically do hand optimized libraries. That's what everybody do to get high performance. In fact, you go out there, there are hundreds of libraries written by manufacturers of processors, different vendors, open source libraries that is trying to give really high performance as much as possible. And this is where most of the time when you want high performance, people end up. The reason this works is these libraries can take the most important set of kernels and implement those kernels. And you can build more complicated functions by composing these kernels together. So this is the ultimate part in actually computer science to this composition is what we can build very complicated programs out of. And so what you can do is these kernels can be taught as black box functions. They can be implemented by hand, domain-specific compiler, or any other way you can do that. And composing them, it's opaque. You don't have to know how that got implemented. You can do that. So let's take an example. So here's a very simple function. These functions take 2 vectors and do outer product of those vectors and get a matrix, scale the matrix, and then accumulate into the original matrix but also scale the original matrix out. This is a common enough function, and we want to run this, and of course, where it run matters. So, I want to run it on an Apple machine. In fact, I want to run it on a M1 chip in here, because we have heard that M1 chip has lot of built-in accelerators. Of course, Apple had told anybody what's in there, but there's a lot of cool things supposed to be in there. So, you want to do that. So, how do you do this? Luckily, there are a couple of libraries there. There's like the ARM performance library written by ARM. They probably not have access to all the Apple hidden secrets in there, but they know enough of the ARM processor, because it's ARM based processor, they can do that. And also Apple has Apple Accelerate library to run this kind of code. So, if you get the ARM performance library, luckily this exact function has implementation. So, you can go there, find that exact function call, figure out how the arguments are, and that's all you need to do. You are done, you get in there, really great. However, if you look at Apple Accelerate library, it's a little bit smaller, it doesn't have this exact function in there. But what it has is two different functions, that one function that do the outer product and the one function do the accumulate. So, not bad, I can just put them together and I can get the exact performance in there. So, I just have to compose two highly optimized functions and you get there. But there is a small problem in here. When you run, the performance is not the same. The Apple Accelerate library is about 30% worse than the ARM Fuse library. So, in fact, the low is better because low runtime in here. So, what is happening here? Why is it that some using very highly optimized one kernel versus two, you have performance difference? So, one possibility might be the most computation time is going to do this outer product. Outer product is slow in the Apple Accelerate library. So, let us go look at Apple Accelerate library outer product. No, its outer product is really fast, because outer product is a very important function, and I think really good programmers in both companies have really implemented it well. So, this is doing really, really well. So, that is not an issue in here. So, what can be the issue? The main issue there is, when you call these two functions, the first function will run through the entire tensor, and by the time you are done, large part of the tensor is outside the cache, and the next thing has to all load in back in the cache. So, there is a lot of cache misses happening between those two. So, that is why you have a 30% overhead. So, one solution might be to say, hey, let us go fix the Apple Accelerate library in here. It is a very simple fix, just basically do the multiply, just instead of just storing it, just multiply the scale the value and then add it in there, store it in there. Simple fix. The problem is, I do not have access to this library. It is very super secret thing that it is calling this even unspecified accelerators in there. I do not know what it is even doing. So, I cannot do this in here. So, what solution do I have when I can't go modify a library? One thing is, instead of running this for the entire data set, I can chunkify the data. I can say, hey, instead of calling the entire matrix, I can call it to multiple chunks. So, what I can do is, instead of this code, I can create bunch of small tiles, column tiles in here, and then basically call each tile by tile for the first function, and when it is done, feed it to the second function, voila, you get the results, and you have a chunkified code in here. You can do that, and then you can iterate through all the tiles in here. Intuitively, now we are doing lot more function calls. So, you can think the function call overhead might be bad. Oh, by the way, this is what you call fusion. Okay, we knew that for last whatever 40, 50 years to do, but now here is a case that we are doing that. And what we find is, even there is function call overhead, this actually get really good performance. So, what that does is, because the chunks are still in cache before the other thing is called, I do not have the cache problem in here, I get the overhead. The second observation is, naive function composition result in locality losses, because you run the entire thing to the end, and then you when you do that, your cache, you have a lot of cache misses, is not good. So, can you do some simple composition? So, what you have to do in this case is, instead of running the entire thing, I basically run this in small chunks. So that I have to have the entire column and part of the row, and produce and basically produce chunk of that and keep doing chunks in here. And if I can do that, I can get this chunk execution. The issue is right now I have this black box 2 implementation. That's not that is possible to do this chunkification. So one possibility you can think is, instead of doing this black box thing, you can basically build a large monolith to deal with everything. Perhaps build this one high performance compiler that compile them all. In fact, this has been the pipe dream for a lot of us. This is what I tried to start in my graduate program when I was a graduate student way long ago, trying to build this kind of monolith compiler. We still haven't been successful building that. We can't have compilers. The only thing we can do like something like that is very domain specific, very narrow things, but the monoliths can't get this kind of performance. The other thing is, we write a library that has everything everybody needs. Every function composition is in there. The problem is there's probably some scientist sitting in some lab somewhere that needs a very weird combination to solve their differential equation. And if you combine everything, you're going to have a gigantic library. This is not practical either. But one of these two observations came about. We know how to do this black box individual kernels and basically compose them. Only problem is there's some locality loss. The question is, can we maintain that composability using black box functions that we know how to do well, but without playing basically the performance engineers can do this, but without playing that cost that we have to incur for locality. That's where Fern comes in. So Fern is a system we built. It's a very minimalist system. What it did was it enriched the normal function interface. So it's not going to touch what's written in there. We the additional function interface. By using that, we can fuse this code and get rid of that locality. Can we work on chunks in here? So let's show a little bit what's happened in Fern. So we have to extend this function interface. So the idea there is, I will tell you how to operate on small chunks of data. So here what I can say is, I am doing some data starting at 0, 0, length 2, 2, or length 4, 2, different lengths in here, I can describe that. In fact, if you have more complicated functions, because we are doing this kind of recursively, you can actually compile this and do subset decompositions and come up with hierarchical decompositions of that to describe what's going on. So if you have something like matrix multiply, this is the additional information you have to say. What you have to tell it is, what I am going to do is, I am going to produce this block. To produce a block at xy location with a length x, length y, I need these additional things from A and B. That is one function. That is my data use relationship. And I need a row, I need a column at these places. If I get those two, I can produce that. Then to get all the data, I have to iterate through these blocks, and if I do that, I can calculate the entire matrix in here. And on top of that, I have my previous just description of the function interface in here. That's all I need. So let's go back to our original example in here. So this is what you will see today. You have the interface description for the function. We have to add some additional information that says, here's the producer-consumer relationship in here. And this is basically added to the include file as annotation in here. This is one additional thing we need. And the next thing we have to do is, this is my original function. I have two matrices, two vectors. I doing these two operations back to back. I need to include some additional information around it to say, this is a little bit of glue logic, and say, okay, create these Fern objects and combine them together to run as a one fuse function in Fern. This is all you have to do in here. So you get those things together, and the Fern system basically takes these two, and optionally you can also give a little bit additional scheduling information if you want. And it will do few very simple compiler passes. This is not a full compiler. We are just doing very outside thing in there. And then it will generate a small glue logic that will basically execute these two functions in a fuse fashion in there. And that's what you run here. So that's what we can do. So let me tell a little bit about experiments in this system. So, Intel has this one DNN library that do convolution. So, you can build a DSL that actually do all this fusion, do all these operations and get really good performance. But instead of doing that, you can have very simple convolution, very high performance convolutions implemented, and then get Fern to do this fusion and get good performance in here. Here's another function we could do. This is the same thing that I show at the beginning, but that now you are adding two other matrices to that too at the end of it. It's a much larger function. And the thing about that is nobody has implemented this function in their libraries, because this is probably some graduate student in some corner. It's only one person in the world who probably want to run this function, so it won't be in the library. But if you try to do normal compositions, even trying to hand fuse them, you're not going to get good results. And then in Fern, we can do a much better fusion and get the best possible result in here. So these are what we show as a simple element-wise fusion in here, but Fern can do more. So for example, if you have something like a blur, the X-blur will take in multiple elements out of a row and produce one element. And a blur Y will take multiple elements out of a column and produce one element. And you want to work that together and do blockwise that. In order to do that, there are a bunch of overlapping inputs that you need to deal with, and the Fern description, producer-consumer relationship, can capture that combination in here. And in fact, if you look at a halide, it's kind of a monolith DSL that can deal with this kind of fusion within the DSL. But instead of doing that, I can have a highly optimized row X and Y convolutions, and then basically merge them together to get this using Fern in here. So all these things you can assume, yes, you can build a DSL, it's in the same family. But you can do even across domains. So assume I have a database that I am retrieving a bunch of data, and I am going to run a sigmoid function in there. Normally what happens, the database will give you the entire data, and then you run the sigmoid in here. So again, the cache problem at risk here. So no database will implement all the functions you want to run with data, so you can't expect that. And the sigmoid library will never implement the database, so you can't expect that won't be in a single DSL. But in here, you can get these two different functions very highly implemented, optimized, and then use Fern to basically fuse them together and actually get nice performance in here. So this is great. It's a great story I show for, but there are places where we fall short a little bit. So here's an example in ISPC where, because it has a DSL, it's doing way more than just fusing for caches. It's actually doing vector level vector reuse in here. So Fern, we can't go to the vector level and register level and do register fusion. So they can do register fusion, and by doing that, they can get better performance. So that is a place we can't, at a black box level, we don't have access to the register level, so we can't do that. So there are certain things we can't get in there. So it's not a complete panacea, but for many cases, this can be very useful. So where I started is with this question. Can we build a system that still maintain that opacity and separate created functions and compose them without having any overhead? What we came up with, yes, we can. Probably a couple of election cycles ahead, this would be very cool. So what we have done is we have built this Fern system. It's available online, and in fact, there's a newer interface than what's even in the paper in this system that I think is better. And you can go find that there. So what are we working next? We are all in CPUs, so basically what Rohan talked about, we want to go to GPUs. GPUs are actually a lot harder because CPU programming is always take CPU as a virtualized unit. Two things can coexist, time multiplex in there. Only thing perhaps you might not want to give all the processors to each. There might be a little bit that you might to share, but mostly it works together. GPUs on the other hand assume when you run something, it owns the entire damn thing. So running two things within is not that easy. So this is a much harder problem. I don't think we can do it completely transparently. because we need to know because which memory it is in, what resources it owns matters in low level. You can't virtualize these things, but composition is still very important. So we are also working on how to figure out composing on GPUs. Okay, with that, I'm done.
Hello, Konstantinos from UCLA. Fantastic talk. Yeah, I really believe this, that, yeah, there's a lot of black box composition programs out there and we need to improve them without like going in the black box components. I was wondering about one thing. How complex and how much effort do these annotations or specifications on the functional interfaces that you need to add? How much effort did it take you to write them, or how complex were they, and so on?
So for many things, lot of functions are very simple. They are doing almost element-wise things are very simple to deal with. Those things are, I think we can even do lot more automation in there. Then there are next set of functions where what you have is you have lot more complicated data use patterns in that. Okay. Again, they are doing independently. That we can do. The third level of complexity there are internal dependencies. There are orderings that has to happen internally because there are you can't just do it any order. Those things we can't do that yet because so there's a cliff when that happens, because if right now we figure out the ordering of running these blocks, they have to run independently and they need to produce the same result. But if there's internal state within these functions, black box functions, then we can't do that easily. So I think right now I feel like we are writing more code than necessary. I think we, for most common cases, 90% of the cases, I think this should be a lot simpler to describe that. I think we have more ways to make it a lot more minimal in there. And also, we probably have to do some more work at the other end when there are a lot more complicated functions that has internal state, internal dependencies, to see whether we can capture that. Those things we haven't gone there, because that to get to that level, I think you need to know something about internals in there. And our hope is, in fact, the person who writes the function should write that interface. Okay, and then the compiler is like, then if it become a standard, like right now a .h file, then the combination would be easier to do.
All right, we do need to run to the next speaker, so maybe, yeah, exactly. So let's thank the speaker again.
Thank you.
Okay, so the next speaker is Alonso Rodriguez from Universidad de Coruna in Spain. So he'll be talking about modular construction and optimization of the UZP sparse format for SPMV on CPUs.
Yeah, it seems okay. Okay, thank you too. Let me put the timer here. Okay, should work. It does. Can you hear me correctly? Okay, fantastic. So let's start. Hi, well, you already presented me. I'm Alonso Rodriguez from Universidad de Coruña from Spain. Today we are presenting this work, the modular construction and optimization for the UCP sparse format for SPMV on CPUs. We are doing this in collaboration with the Colorado State University too. And let's get started because we will need some time here. So the main idea we had is to encode the non-zero coordinates using integer polyhedra and affine lattices so that we can use regular loops for computations. Traditionally, what we did was store those sparse matrices in CSR or COO BCSR matrices, which basically we just store the data separately from the indices, which are stored in integer arrays. Our approach here is to encode these sparse coordinates directly with polyhedra, storing its structure, and thus using a generic but also tunable executor that only uses regular loops and so avoids any use of interaction arrays. This makes our new approach both modular, tunable, and kind of sim-dish depending on how we export it, and also general because, well, now we are going to work with matrices, but we can also extend that to tensors. So up there you have the traditional CSR SPMV loop, and on the X here, I don't know if you can see my cursor, you can see like here we do have that double indirection code, which makes it very difficult, if not impossible, to do gather-scatter operations, so we cannot vectorize it easily. And down there we have a simple specialized code for that matrix. In this case, a matrix could be a tensor. You have on the bottom left, so the red dots would be non-zeros, and so this specialized code is specific for this sparse matrix structure. Not that data, we could change the data, but not the structure, and it computes and accesses only those red dots. But what is a polyhedron, you may ask? So let's start with a matrix. A polyhedron is basically a region in space. In this case, we are dealing with integer polyhedrons, so this would be a two-dimensional polyhedron, and we can see this list of points as a square. This will be precisely the COO notation. It's not compressed. We can compress any of those dimensions. So we can also have this alternate description, which would be the polyhedral one. Here we have two inequalities here, and the polyhedron is described as the intersection of these two half planes, expressed as such inequalities, and the points that lay inside that intersection are the points that are inside the polyhedron. So in this work, we will only model a polyhedra with integer points, and the question is, can we do more complex shapes? Yes, of course, we can. For example, if we want to tilt the vertical lines, this way we can do a diamond. We just need to add a little more restrictions to that shape of the polyhedron, and we can almost note any closed region of points in space. However, we do have a problem, which is what do we do with holes? If we want to represent this structure, for example, which would be very usual in some sparse matrices, depending on how we obtain them, we cannot do that. So that's when the C comes in. So we do intersect the image of this polyhedra with an affine integer lattice, and what we are doing basically here is having a 2x2 square, and we are just scaling it, adding a stride to the points it traverses. So that's the definition of a C polyhedron. So yeah, basically it can have holes. And also, and very important, this is a key message I want you to take home from this presentation, is that polyhedra, although it's a precisely defined mathematical concept, can be interpreted and viewed as different things. We have it like this C polyhedra is a collection of points, but we can also define it as a sequence of traversal. Like, for example, we do have here 2 for loops that exactly map to the values in these inequalities and also to the values in the integer lattice. And so we will be dealing with this view of for loops equals polyhedra from now on. So this seems a little bit like the concept is simple, it's understandable. We are just mapping domains and iteration domains basically, but this is not easy at all. So basically, let's have this HB CAN 1072, which is a medium-size matrix from suit sparse, and this can be represented with 870 polyhedra of up to 8 dimensions. But let's remember, 8 dimensions, unless we do loop fusion, but we are not going into that detail, should be represented with 8 consecutive, like nested for loops, which is sometimes not good. So what we are doing to do now, our approach is use more polyhedra, but of lower dimensionality, usually dimensionality 1 or 2 at most. In terms of speed, because well, we are in the HPC conference, so we do scale quite well. We can reconstruct matrices with 100 million non-zeros in a matter of minutes, and our time scales almost linearly in terms of non-zeros. So we do perform quite well in that regard. And our way of working will be just mine for simple patterns and then tune it later. I will show you. So C polyhedrons and polyhedra have been around for many years. These are like a very usual concept in mathematics, but they are not new for us at all. In our research groups, we have explored this firstly in here at PLDI'25 with the DSCG sparse matrix multiplication. What we did was basically take a sparse matrix and then create an ad hoc binary so that it performed all the necessary operations, all one by the next one. So it has some, like the only pro we found there is that we found a way to do that without using integration arrays, but there are several cons. The first one is that the binary size is huge, so it's basically proportional to the size of the matrix. And then from that come some other problems, like we flood the instruction cache because we are dispatching a lot of instructions. And also we don't, well, we technically could auto-vectorize because it's just a sequence of FMAs. But if you have ever tried to compile 100 million lines of code with GC, usually it's segfaults. So we just proved that that was a concept and that was feasible. Next, we iterated on it with Macbeth, which is the fastest we have found in the literature. And we implemented a two-stage scheduling approach. Firstly, we mined for the patterns, just as the previous paper, but then by modifying the compiler, we managed to emit AVX code, so we had a significant speed up over in some places, as you will see next. So in this work, what we are trying to do, and what we successfully do, is have the best of both worlds, have also the separated data from the executor that we have in CSR or other structures, while also leveraging the performance of Macbeth without the need of a specific binary for each sparse structure. So for that, we do have a 4-step plan. The first thing we need to do is define a UCP sparse format. UCP stands for Union of C polyhedra sparse format. This format encodes C polyhedra shapes in the dictionary, just the different ones, and then a list of origins, which are instances of those shapes, and we store like the beginning point of them. Then we developed a tool called C polyhedrator. There's no C for verbs for some reason. It's a Rust-based tool that quickly mines for C polyhedra, for only a small C polyhedra, from a matrix market file, and then we use tuners, and tuners are key for this to work, because from these tuners, we will see later, we will make the performance go up. So given this, we'll have some generated executors, also maybe produced by tuners. In this case, yes, they are. And in our experiments, UCP outperforms on average all baselines tested for SPMV on CPUs, both single and multi-core, both cold and hot cache, except for Macbeth. Our workflow pipeline will be like this. We would take an input matrix, and we'll pipe it through, we would send it to C polyhedrator with a user-defined pattern file for it to mine for patterns. Then we would use a tuner, although it is not necessary. We could just take the UCP file and send it directly to the generic executor. Or we can take the optimized UCP file, pipe it through an optimized generic executor, and perform any sparse operation we want to perform. In this case, we are just performing SPMV. This would be an example synthetic matrix we have created, and we have both the CO and CSR formats here. And to compare that, we have down there the UCP sparse format. What we do is we find these polyhedrons, find these shapes. I will use these words interchangeably. And we find 3 different shapes with 4 instances of them. So the shape 1 would be the green one. We can see we have 2 instances of them. We also have shape 2 and shape 3, which will be red and the black one, although these are not that important. And also we have 2 dangling points. What do we do with them? So with these dangling points, what we do is encode them in the most optimal already existing representation. In this case, it's COO, but it could also be CSR depending on the layout of these points. But we are not limited to this. We have another thing which we can do is just represent these as length 1 polyhedrons, and this has a very interesting side effect because we do have pretty interesting compression ratios while also having constant time insertion, because what we need to do is basically just at an origin. If you do that repeatedly, the performance will drop, but it will still work, no need for recompression or re-exporting anything. We also can do here And I will be a little bit fast here because we don't have that much time here. We do have these two instances of the same shape, so we can think of these. Remember the Polyhedra explanation? This is basically a 2x3 rectangle, just with a very big lattice between them. So we do encode this as 0, 1, 0, 0, 1 meaning from 0 to 1. So that will be the vertical dimension. Then we have from 0 to 2, that will be the horizontal dimension. And here we will encode the affine lattice. That will be 9, 0, 0 for the vertical stride and 0 to 0 for the horizontal ones, as well as the singular points, but we are not going into detail here. Here we have a mapping for SPMV code, but we are not going to detail either because these slides are for a 40-minute talk, and this is not. We do have not 40 minutes. So now that we have set the basics for the UCP sparse format, we need to achieve some performance. And to achieve some performance, the tuners are key. We have implemented 3, but we do encourage any users that want to try this to implement their own tuners. And these tuners, what they do is, well, it says there's the explore alternate but equivalent representations of a sparse structure. Basically, the technical name is the explore equivalence classes, or they just change the way the points appear on the file. So firstly, we have the aggregation tuner. So let's assume we do have 2 shapes of the same characteristics, for example, 2 horizontal lines. And those 2 horizontal lines are contiguous to one another, so we can basically merge them. We do have 2 of length 8, we can merge them into of length 16. That is very important because that allows us to mine for patterns of reduced lengths, thus avoiding complexity explosion, and then merge them afterwards. Also, we do have the favor locality tuner, which reorders the way the origins appear in the file. So what this allows us is to have great cache performance, like to have a lot of cache hits both in the input matrix as well as in the output vector. And also we implemented the specialized dictionary, which is the only tuner that doesn't modify the UCP file itself. What it does is, let's say we are working with a specific set of matrices. Usually, unless we're doing like random or very synthetic matrices, our matrices do have some kind of regularity. For example, if we are extracting the data of something that is symmetrical, we'd have symmetrical matrices. We may have the major row fully populated. We may have some bands here and there. So we usually have some similarities between those matrices, and we can use that to generate specialized tuners, which shouldn't be confused with tuners that only work on those matrices. They are still generate tuners, but they are tuned specially for our type of matrices, and the amount of speed that we obtain from that is pretty significant. So for our experimental setup, we selected all of the 2,754 matrices from suit sparse, and we did a representative selection of them. So here we have plotted every single one suit sparse matrix, and with crosses, we have selected these are the selected ones. And as you may see, we have no particular bias towards any region. It's pretty representative of the whole spectrum. And also in the bottom left part, you can see a relation about the diagonality of the matrices. So we are not limited. So we basically do not do any kind of toy matrices or just diagonal matrices or any matrix that can be represented with a diagonal format. We do real-life matrices taken from suit sparse. And these are our results. So few notes here because there's a lot to explain here. The first what we can look at the top right is that vanilla CSR is clearly bandwidth limited by the memory. And secondly, we can note here that our peak performance, although not the average, is very near the theoretical limit of the bandwidth itself. To put into perspective, the HPCG benchmark in this particular machine maxes out at 5.4 gigaflops, and we are achieving 9.21 with an average of 2.330. We also compete against CSR5 AVX2, which is a very popular algorithm out there in the literature, and also against PSC from Toronto, it's for partially destroyed codelet. And we basically max out this bandwidth speed. We also max out the bandwidth for this particular machine in 1-core double precision gold cache, which would mean just one iteration of the SPMV loop. But we do have some other more data. Here we also get better averages and peak performances against all of the other compared. In this case, we are doing 8 cores, double precision and hot cache, which would mean several iterations of the SPMV loop, and it doesn't necessarily mean better cache reutilization, but if programmed properly, we do have a lot more of cache hits, and thus improved performance. I want to say, I was supposed to say in the previous one, but I forgot. Every single point we have found we have plotted here, especially the BCSR1, because well, we can use block size between 2 and 32. We also can enable or disable tuning hints. All of these have been maxed out. So if basically for a single matrix, the best performance was achieved with tuning hints and 16 block size. That's the one that we have plotted. We are not cherry picking any data. And in general, we provide the best overall performance over every single other format, but, and a quick, very important disclaimer, although we are better in some cases, much better in some others, and the same in others, maybe worse, it's still important to note that if you are aiming for the top 1% performance, at the end of the day, what you need to do is still find the best suitable format for your specific case. It might be UZP. Our measurements show that for much more than half of the matrices it is, but for some others it is not. So you should be aiming for that if you're into that kind of performance maximization. So very quickly here, we are also comparing against ourselves, against Macbeth, which does have a very similar way of working, but with a very different philosophy. We do not outperform Macbeth on average, although we do have much higher peak performance, but it's just for a little amount of matrices. And also, we are not that strong against Macbeth in the median sizes. We are talking about 10 to the 3 to the 10 to the power of 4 non-zeros. Here, Macbeth is not also achieving higher average, but also the consistency is much better than UCP, which is all over the place. And finally, I want to show you here a little graph, which is not very easy to understand. So the green part is the uncompressible data. If we are doing lossless compression, this is the part that we cannot compress, which is the data itself, the values of the non-zeros. Then in blue, we would have plotted the UCP metadata itself, the patterns and the strides. And in yellow, we have the dangling points, maybe data represented by CSR, COO, which is multiplied well with its corresponding algorithm. And in red, starting from 1, would be the multiplier if we did not have this special region. So that's it. I hope you have found this talk interesting, and for a take-home message, we have successfully alleviated the limitations of our prior work using C polyhedra, and we are also distributing the UCP sparse format and the associated complete toolchain to build, tune, and compute it. You can find that in our paper, and it's also up on GitHub. We encourage the users to program their own tuners if they need it for their own workflows, and that's it. I am very thankful for your attention. I'm more than happy to answer any questions or even offline. So thank you very much.
Any questions?
Kazan from McMaster, very interesting work.
Thank you.
One quick question is, how would this be extended if you apply data transformation? So you are finding a bunch of patterns and you model them as a polyhedral. So I believe like right now you just see it as a CSR, but what if you want to actually do the transformation? How would that change your approach?
Data transformation, you are speaking about modifying the sparse matrix itself, right?
Yes.
So we are basically, right now, we are targeting constant, well not constant, but constant structure matrices. I am not a physic, so I don't have the details, but I'm aware that it's useful for Hamiltonians and such things. Maybe conjugate gradient also benefits.
Oh yeah, for
largely.
sure. No, my point is like if you are allowed to restore the matrix.
Yeah, totally. But you would need either to re-export or retune the matrix if you want to have performance, but you can totally edit the matrix on the fly. So you can both add non-zero, but just appending it. Or you can also remove a non-zero by either altering the polyhedron or just putting a 0 there. It's still valid data. And also, yeah, that's basically it.
Have you seen any benefit of doing that?
Any benefit? Right now we have not tried doing that, I think, at least not me, because we are working with the Colorado State University too. We are trying right now the implementation in GPUs. We have some results, but I cannot assure anything, so we're still working on it. Also SPMM, we are still not strong on them, but because it depends on the way you tune and you export the code, we may have some results.
Great, thanks.
Thank you.
All right, let's thank the speaker again.
Hello, my name is Roy Margarit, and the name of the talk is Dynamic Robustness Verification Against Weak Memory. This is a joint work with Michalis, Shachar, and Ori. So, as we all know, concurrency is difficult. Bugs are difficult to find and reproduce, and static verification does not scale and does not allow us to find all the bugs easily as the size of the programs grow and grow. The practical solution to this is dynamic race detection. And we say that when two threads access the same variable concurrently, and one of them is writes, then they race. And the dynamic race detection allows us to test for races during an execution of a program. And it's such a prominent option that dynamic race detection is incorporated into the GCC and LLVM compilers in a pass called TSAN for thread sanitizer. Now, existing race detectors assume for sequential consistency, where synchronization happens through locks and atomic variables, and all other races are bugs. And this is what they try to find. In practice, languages like C and C++ have a weak memory model. The atomics provide weaker synchronizations, such as release, acquire, relaxed, while fancies are used to fine-tune the synchronization to actually get the stronger behavior. So let us consider this example for a moment, called store buffer. The left thread is going to write 1 to an atomic variable x, and then read the value of y, an atomic variable. And the right thread is going to write 1 to y and read the value of x. And under sequential consistency, it is not possible to read 0 for both x and y. Since, for example, if we first execute the left thread, then we write 1 to x and read 0 for y, which is what we want. But then we have to write 1 to y, at which point we are going to read the value of x, but it was already overwritten. So we have to read the value 1 for x instead of the initialization value. But under the C and C++ memory model, this kind of behavior is allowed. And the reason is because we don't want to work with the memory directly. We would like to utilize caches. So both of the writes are going to write to the local cache of the CPU that's executing this thread, while the reads are going to read from the memory. And the written value did not propagate to the memory, so we can actually read the stale value of 0. And the problem is that existing race detectors do not find races that depend on this behavior due to observer effect. They introduce their own synchronization to try and track for races, and in such a process, they cannot actually identify this behavior. And thus, if we have behavior that depends on this, such as accessing a non-atomic variable n and writing to it from both threads, we actually have a race that's going to trigger undefined behavior. But our race detector is not going to identify it because the race depends on the weak behavior of the program that we cannot see with the race detector due to observer effect. So one way to try to solve this is by simulating the C++ memory model to make sure that we get everything correct. And doing so is difficult. And even if we can succeed, the price is going to have to be paid. Either we're going to end up with an unbounded memory overhead that's proportional to the execution length, because we might be able to read from some arbitrary location and we need to worry about reading from there, which is the approach done by C-learn tester. Or we're going to have to sacrifice our completeness with regarding to the C++ memory model. This is what TSON11 does. And our contribution is to propose to complement the standard trace detection with dynamic robustness verification. And we say that a program is robust against C++ if and only if all the allowed behavior it has under C++ are those that are possible under sequential consistency. And in turn, if we prove the program is robust and verify that it does not have any races assuming sequential consistency, then we actually proved that it does not have races under the weak memory model. And thus, we are actually able to make sure that our program is correct. And robustness verification is immune to observer effect, because establishing robustness only requires the sequential consistency semantics. And in such case, we don't actually need to simulate or worry about all the weak behaviors. Additionally, we developed a technique called RSON for robustness sanitizer to verify robustness dynamically. RSON is sound and complete, so if there is an execution we encounter that has non-robustness witness, we are going to report a robustness violation. And if the program is robust, we are not going to incorrectly report it as non-robust. Additionally, it consumes linear memory in the number of threads and atomic variables, regardless of the execution length, so we can have unbounded loops and it is not going to affect our memory utilization. And RSON scales to real-world programs and allows defensive programming in C and C++. And to understand the way we do this is using non-robustness witness, where a theorem previously defined was that a program is robust if and only if non-robustness witness does not exist for the program. And to understand this, we need to understand that there is an happens before relation, which is a partial order between memory accesses that happen during the program execution, denoting possible the synchronization that happens in this execution. And each memory model has its own happens before relationship. So the happens before for C++ is going to be a subset of the happens before for sequential consistency, as the sequential consistency model is going to enforce more synchronization that happens. And the non-robustness witness is basically a sequential consistent trace in which the happens before for C++ and sequential consistency can diverge. And if I want to be more precise, it's that some thread T is about to access location X. And the last write to X has an HBSC, but does not have HB C++ to this thread, which then denotes that the behavior of the program can diverge at this point. And to see how we do this, so let us consider again the same example that we had before. So let us consider a specific execution, one that we first execute the left thread. We wrote 1 to X and then read the value 0 for Y. And then the second thread is going to write 1 to Y and read the value of X. And we note that between this read of Y to the write of Y, it has to happen under sequential consistency because we read a value and then overwrote it. So any later write must have happened after we read the earlier one. But under the C++ memory model, we don't have an happens before relation because there is no causality. Nothing happened enforces an ordering between this read of 0 and this write of Y of 1. And so this point where we are about to execute X and read a value is a non-robust witness because under sequential consistency we cannot read the value 0, and under the C++ memory model we can. So the key idea is that we can identify and predict non-robustness witnesses dynamically. And we do this by using location clocks, which is a novel variant of vector clocks, where each location is going to have a timestamp in contrast to vector clocks, which give timestamps to thread IDs. And our instrumentation assigns these location clocks to threads and locations and allows us to track everything. So the way we do it is by having a TSC, which is a location clock that tracks the per location maximal timestamps that have and happens before SE relation to this thread T. So we know what is the maximal timestamp that the thread knows of for each location in SC. And additionally, we have T C++, which does the same thing, but with the C++ memory model. So we track what happens before in C++. And for this example, we note that the timestamp we're going to have for X for the right thread under sequential consistency is going to be higher than what we have for C++, indicating the fact that the sequential consistent model is aware of a later write that happened while the C++ model cannot, and thus the program's execution can diverge at this point, and we report a robustness violation. Now, the way we maintain this instrumentation is using a couple more vector clocks. So location clocks, WSC, which is a location clock that tracks per location maximal timestamps that have and happens before SC to the latest write to X. And similarly, WC++, which is a location clock that tracks the per location maximal timestamps that have HB C++ to the latest write to X. So what is the latest timestamp that each memory location is aware of about any other atomic memory location? And additionally, for the sequential consistent part, we also need an MSC, which is a location clock that tracks the per location maximal timestamps that have an HBSC to an access to X, which is where we're going to see the synchronization from the earlier example under sequential consistency. So let us consider how does it work. So first we're going to need to keep the value of what is the timestamp for X under the latest write of X, which is going to be the maximal one. We're going to have to keep what does Y know about latest times of X. What does each thread know about the latest write of X under the sequential consistency model, and what does each thread know about the latest write to X under the C++ memory model. And we are going to simplify the example and only keep things that we need to actually understand, but the entire thing is a bit more complicated. So we are going to try and execute our write to 1 to X. So what we're going to do is update the timestamp that we have for X, and it's going to be 1 instead of 0, the initial value. And then since the left thread executed this write, then it's going to be aware of the latest timestamp for X, both under sequential consistency and under the C++ memory model. So they both end up as being X at 1, timestamp 1 as well. And now we are going to read the value of Y, and the value of the memory right now is 0. So we're going to read 0. But as a side effect of reading the value, we actually propagate the fact that now the latest access to Y knows of the latest write that happened to X at timestamp 1. So when we are going to now try and write the value of Y, we actually need to update the fact that now the write thread under the sequential consistent model knows of X at time 1. But under C++, because there was no causality, we do not get to update this value, and we still have this 0. Finally, when we are going to try and read X, we note that the timestamp we have for X under C++ memory model is smaller than what we have under sequential consistency, and report the robustness violation as we have a non-robustness witness. Additionally, an important advantage for location clocks is their ability to predict non-robustness witness rather than just identifying their existence. If we consider this example, which is very similar to what we had before, now after the T1 wrote 1 to X and read the value 0 for Y, there is some other thread, T3, that's going to write 2 to X. At which point, now when we are going to read Y, we are going to have this synchronization, but now when we identify that we are going to read X, we don't have an appendage before C from the latest write to our read. Thus, it does not qualify as the definition of non-robustness. But using location clocks, we can actually identify that it's true that we are not aware of the latest write. But we still have a timestamp smaller for the C++ view versus the sequential consistent one, and still report a robustness violation. And this was crucial for our benchmarks to actually improve the performance and identify possible witnesses, even though they do not necessarily exist in this specific execution. We implemented Arson as a TSAN extension, which is an LLVM pass. We do not require program annotation. The user can just compile their C++ program and be off with it. We support the RC20 fragment of the C++ memory model, so we have release, acquire, relax atomic variables, read, modify, write operations, fancies, and when a robustness violation occurs, we give a full backtrace that identifies the violation, and the programmer can actually use this to fix the possible violation. And in doing so, we also corrected TSAN to support relaxed access and fancies correctly, which it does not support at the time. To check the utility of our tool, we first compared it to the static robustness verification tools, Rocker, and we wanted to know if detecting non-robustness witnesses is going to be faster with our dynamic approach. So here we see an example of an incorrect implementation of Decker mutex, and we see that the more threads we have, the more the static approach is going to take time to find the violation, while our dynamic approach finds it very quickly. Additionally, we wanted to see the memory consumption difference. And again, we see that the more threads there are, the bigger the search space, the more the static approach requires memory, while our dynamic approach does not actually require that much more memory, even though our program gets bigger. Additionally, the fact that we can identify things that static does not say much. We wanted to see if it can actually work in the real world. And can we use Arson to convert programs so they are going to be robust and then can be verified for threads, for races? And our results are going to be better than just promoting all the atomic access to sequential consistency, at which point we are going to have robustness. So one of the case studies we had was the MIM allocator by Microsoft. It's 12,000 lines of C code. It heavily uses weak memory atomics. The test code had 60,000 distinct atomic locations, so it scales. And Arson identified 20 distinct robustness violations, which we repaired one by one by adding fancies and restoring the robustness of the program. And we know that if we were to promote all the accesses to sequential consistency, it would lead to 3 times more fancies than what we had. So we are actually able to get robustness with less amount of fancies and get better performance, since both the hardware does not have to synchronize all the time, and the compiler has more opportunities to actually optimize the code. To conclude, we propose to complement standard trace detection with dynamic robustness verification. Robustness is immune to observer effect, and establishing robustness only requires sequential consistency semantics. Arson is the technique we developed to verify robustness, and we implemented it. It is sound, complete, consumes linear memory in the number of threads in atomic variables, and it scales to real-world programs and allows for defensive programming against the C++ memory models. Thank you.
From NUS.
Give me a second. Okay. Go ahead. and ask the question. Sorry.
Am I audible? Can the speakers hear me? Now we can't hear him. Okay, so Roy, thank you for the great talk. I'm Umang from NUS. Great work. I wanted to clarify two things. So first, are you working with execution graph robustness being your notion of robustness, or is it a more general?
So it is execution graph robustness that we use.
I see. So have you explored the problem of doing dynamic checking for a more for a different notion of robustness?
Have you checked the
have you explored the problem of checking robustness dynamically, but for a different notion of robustness?
No, we did not try a different one. Getting even execution graph robustness was not a trivial task, so that was our focus in this work.
Okay, thank you. And the other question I have is, so initially in the presentation, you alluded to some combination of doing race detection and robustness together. Can you again talk about what conclusion can I draw from robustness in terms of race detection? Meaning, if I find a robustness violation, does it mean that my race that I miss on some races or I find false races? And likewise, if I don't find a robustness violation, what does it mean in terms of races?
Okay, so for if you have robustness violations, that means that for this execution that you found a robustness violation, you might have different kinds of executions that you might not be able to check for races. So you might have races even in your program and you're not going to be able to detect them. And if the program is robust, then you're not having any races reported, then you're guaranteed that at least for these executions and what we can predict from them, that you're not going to have racing.
Could you repeat the question? No, could you repeat the answer? I think I figured out how to
So
set up sound.
until now, you were not very audible. Would you like to repeat your answer?
Yeah. Sorry about that, yeah. Could you repeat your answer?
Yeah, I can repeat the answer. So again, if you have a robust execution, then you're not going to find races, and you know for this specific execution that you've tried and the ones you can predict out of it, that you're not going to have races in the program, so you have this empty. And if you have robustness violations, that means that when you're going to check for races, you're not actually exploring the entirety of the search spaces, so you might have races that you're not going to.
Thank you.
Hi, thanks for the talk. This is.
Sorry?
Was an echo? Was an echo. Okay. Hi, this is Ralf Jung from ETH Zurich. Thanks for the talk. So I was wondering, how common is robustness in practice? Like a robustness violation itself is not necessarily a bug in the program, if I understood correctly, right? So if I just run this on some code and I get a violation, I don't know if that's a problem or not. And like so if I take an actual like concurrency library, like I don't know, some interesting concurrency things in Rust, for example, or in C++, some complicated data structures, will they typically have robustness violations? Like internally hidden from the user, but like as part of the implementation details basically, or is this uncommon?
Can you repeat the question for me?
How common is it? It would be nice to have an actual working audio setup. How common is it to have robustness violations in like typical concurrency libraries that implement concurrent data structures?
The question is how far weak memory is being utilized. If there is relaxed access all over the place, for example, then it's going to be easier to get robustness violations. entirety of the semantics for the C++ memory model, and instead try to go defensively for robustness and still get some performance benefits that you could have gotten for the release require relax stuff, without actually having to have a formal proof verification. In the previous paper in PLDI'19, there was an example that showed that even though professional programmers tried to run some program, it actually ended up having bugs even after one of the proofs, the programs had informal verification, and later on formal verification that just proved different properties than what is required. So it gets really complicated even for researchers and professional developers. So there are probably bugs there if people have robust violations, but if somebody verified it, then they don't.
You come to the front. I think that would be easier. Like when you ask the question. Like here. Yeah. Unfortunately, the microphone is.
Okay.
You have to use my microphone.
Okay. Hello, this is Kun Shan from Australian National University. So I think this is a dynamic algorithm that detect this kind of data race at runtime. But I know that one cause of non-sequential consistent execution, in addition to CPU's reordering, is that the compiler may reorder the instructions in an unexpected way, different from how the programmer has written. So from an implementation point of view, if I assume this can be implemented by instrumenting the compiler, but how could you, if the compiler also reorder the instrumentation, will this let some of the errors slip under this, or do you have a way to prevent this from happening? Thank you.
We can prevent it by instrumenting the program before letting the compiler do its optimizations, or even try to run the program without to compile the program without optimizations and see how well it goes. This is going to let us know from the original program and not worry about the transformed program.
Yeah, but another question: if like we does this optimize this instrumentation force the compiler to compile the code in such a way that after we instrument the program, the unexpected execution will never appear again? I mean, so there's kind of an observer effect that if we install some observation and the bug will disappear for some reason.
So the observer effect is going to disappear during the instrumentation, since we want to verify robustness using sequential consistency semantics. And this is when you don't have to worry about it. But when you're going to have your program later without instrumentation, because it's going to be at runtime on some production system, then you're going to have all the weak behaviors again, but you're still not going to diverge from sequential consistency if the program is robust.
Okay, thank you.
All right, I think with that, let's thank the speaker again. Yeah, and Roy mentioned like he really wanted to be in person, but due to the circumstances, he could not come. Yep. So with that, it concludes today's session on HPC and the first day of PLDI. Thanks.